There is a place at the bottom of the ocean where the water itself is poison, not because of anything that was dumped there, not because of chemicals or waste or human industry. The poison is natural. It comes from the earth itself, seeping up through cracks in the seafloor, concentrating over thousands of years into something that no living creature can tolerate. And when fish swim into this place, they die. Not slowly, not from disease or age. They die instantly, their bodies perfectly preserved in the brine, their scales intact, their eyes still open, their fins frozen in the last stroke they ever took. They become mummies at the bottom of the world, preserved forever in a lake that sits beneath the sea. Let that image settle in your mind for a moment. A lake, at the bottom of the ocean, with shorelines and surfaces and currents of its own. A body of water that is separate from the water around it, denser and heavier and deadlier, sitting in a depression on the seafloor like a pool of mercury at the bottom of a bowl. And everything that enters it dies. This is not a metaphor. This is not a myth from an old sailor's tale. This is real. This is happening right now, as you lie here in the quiet of your room, as your breathing slows and your mind begins to drift. Somewhere in the darkness of the Gulf of Mexico, 3,000 feet below the surface, a lake of brine is sitting perfectly still, waiting. It has been waiting for thousands of years. It will wait for thousands more. And in that lake, suspended in the salt, are the bodies of everything that ever made the mistake of crossing its invisible border. If you find this quiet journey into the strange and deadly corners of the deep ocean something you truly enjoy, I would be grateful if you would like the video and subscribe. It is a comfort to know that there are others who share this curiosity, who want to explore the darkness together. And tell me in the comments where you are listening from tonight and what time it is for you. There is something grounding about knowing that across the world, in different time zones, in different rooms, other people are also drifting through these waters with us. Now let your shoulders drop. Let the weight of the day fall away from you. Take a slow breath in and let it out even slower. We are going to descend. We are going to leave the world of light and air behind. We are going to go to a place where the rules of nature are different, where water can kill you just by being too much itself. The surface of the ocean is the boundary between two worlds. Above it, the world of air, of light, of warmth. Below it, the world of pressure, of darkness, of cold. We know this boundary well. We cross it every time we dive beneath the waves. But what most of us do not know is that there is a second boundary, hidden much deeper. A boundary between water and water. A place where the ocean stops being the ocean and becomes something else entirely. This second boundary exists wherever brine pools form. And brine pools are one of the most extraordinary and least understood phenomena on our planet. To understand a brine pool, you first have to understand salt. Not the salt you sprinkle on your food, but salt in its deeper geological sense. The ocean is salty because rivers carry dissolved minerals from the land into the sea. Over millions of years, these minerals have accumulated, giving the ocean an average salinity of about 3.5%. That means that for every liter of seawater, about 35 grams are dissolved salts. Your body is about 0.9% salt. The ocean is nearly 4 times saltier than your blood, and that is already a significant difference. But a brine pool is something else entirely. In a brine pool, the salinity is not 3.5%. It is not 10%. It is not 20%. In some brine pools, the salinity reaches over 40%. In the most extreme cases, it can be as high as 50 or even 60%. That is 10 to 15 times saltier than the surrounding ocean. At that concentration, the water behaves differently. It becomes denser, much denser. And density is the key to everything. In the ocean, density determines where things go. Warm water rises, cold water sinks. Fresh water floats on top of salt water, and extremely salty water, brine, sinks to the bottom, where it accumulates in depressions and basins like water pooling in a hole. Because the brine is so much denser than the normal seawater above it, it does not mix. It stays separate. It forms a distinct layer, a body of water within the water, with a surface that you can actually see. If you were to descend in a submersible toward a brine pool, you would see it coming. The water around you would suddenly become clear. crystalline. Then you would notice a shimmering effect, like heat haze on a hot road, caused by the difference in density between the two layers of water. And then, below you, you would see the surface of the pool. It looks exactly like the surface of a lake. It reflects light. It ripples when disturbed. It has waves. And it has a shoreline, where the normal ocean floor meets the edge of the brine. And along that shoreline, you would see the dead. The creatures that live in the deep ocean are adapted to the cold and the dark and the pressure. They are not adapted to brine. When a fish or a squid or a shrimp swims from normal seawater into a brine pool, something happens at the cellular level. The difference in salinity causes a massive osmotic shock. Water is drawn out of the creature's cells at an overwhelming rate, dehydrating them in seconds. The creature's gills, its eyes, its internal organs, all of them are suddenly exposed to a concentration of salt that they cannot handle. The creature dies almost instantly, and because the brine is so dense and so still, the body does not decay. There is no oxygen in the brine to support the bacteria that normally break down organic matter. So the body simply sinks into the pool and stays there, preserved, like a fly in amber. Some of these bodies have been sitting in brine pools for decades. They have not decomposed. They have not been eaten by scavengers. They are still there looking almost alive, resting at the bottom of a lake beneath the sea. The first time scientists saw this, they could not believe it. It was the 1960s, and oceanographers were just beginning to explore the deep ocean in submersibles. They were mapping the seafloor of the Gulf of Mexico looking for oil and gas deposits when their instruments detected something strange, a layer of water with an unusually high salt concentration. They followed the signal to its source, and what they found changed the way we think about the ocean. They found a lake, a real lake, 3,000 feet below the surface, with waves and shorelines and everything that implies. And around its edges, littering the seafloor like fallen leaves, were the bodies of deep-sea creatures that had ventured too close and paid the price. Since that first discovery, brine pools have been found in oceans all over the world. In the Gulf of Mexico, there are dozens of them. In the Mediterranean Sea, there are entire systems of brine lakes and rivers, flowing along the seafloor like underwater versions of the Nile. In the Red Sea, there are brine pools that are among the hottest and deepest ever found, their waters superheated by volcanic activity below the seabed. In the Arctic Ocean, in the Southern Ocean around Antarctica, in the deep basins of the Indian Ocean, brine pools have been discovered, each one unique in its size, shape, salinity, and temperature. And every single one of them is a dead zone, a place where life, as we know it, cannot exist. But here is the strange part. The part that makes brine pools not just a curiosity, but a profound scientific mystery. Around the edges of these deadly lakes, life does exist. Not in the brine itself, but at its border. Along the shoreline, where the brine meets the normal seawater, there is a thin zone of mixing, a gradient where the salinity changes from deadly to survivable. And in that gradient, some of the most remarkable organisms on Earth have learned to live. Microbial mats, thick, layered communities of bacteria that thrive on the chemical energy released at the interface between the brine and the seawater. These mats are like nothing else on Earth. They are ancient, they are strange, and they may hold the key to understanding how life began on our planet. Because brine pools are not just lakes of death, they are also windows into the deep history of the Earth. The chemistry of these pools, the extreme conditions they create, the way they preserve organic material for thousands of years, all of this makes them a kind of natural laboratory, a place where we can study what happens to life when it is pushed to its absolute limits, a place where we can see, in real time, the processes that may have shaped the earliest living things on Earth. And that is what we are going to explore tonight. We are going to descend into the deepest, darkest parts of the ocean to visit these underwater lakes. We are going to learn how they form, why they kill, and what they can teach us about the origins of life itself. We are going to see the bodies of the creatures that have fallen into the brine, preserved like statues in a museum of the deep. And we are going to wonder at the strange, beautiful, deadly world that exists just beneath our feet, hidden in the darkness of the abyss. So let us begin. Let us leave the surface behind. Let our descent carry us down through the cold and the dark and the silence, down to a place where the ocean itself becomes a killer, where water becomes a weapon, where a lake waits at the bottom of the sea. The first brine pool was discovered almost by accident. It was the 1960s, a time when oceanography was still in its infancy. We had mapped the surface of the moon more accurately than we had mapped the floor of the sea, and the technology for exploring the deep was crude and dangerous. Submersibles were tiny, fragile spheres of steel, lowered on cables from ships, carrying 1 or 2 men into a world they were never designed to inhabit. The discovery happened in the Gulf of Mexico, a region that was already known for its unusual geology. The Gulf sits on top of a massive layer of salt buried deep beneath the seafloor. This salt was deposited millions of years ago during the Jurassic period, when the Gulf of Mexico was a shallow sea that repeatedly evaporated, leaving behind thick layers of salt. Over time, those layers were buried by sediment, compressed by the weight of the rock above them, and transformed into the geological formation known as the Luan Salt. This salt is not stable. It is less dense than the rock above it, and over millions of years, it has been pushing upward, squeezing through cracks and faults in the seafloor like toothpaste through the gaps in a tube. When the salt reaches the surface of the seabed, it begins to dissolve. But it does not dissolve evenly. The salt forms structures called salt domes, which rise like mountains beneath the sediment. And around these domes, something remarkable happens. Seawater seeps down through the cracks in the seafloor, reaching the buried salt deposits. The water dissolves the salt, becoming saturated with it. And then, because this saturated brine is so much denser than normal seawater, it does not rise. It sinks. It flows downhill along the seafloor, following the contours of the ocean bed, until it collects in depressions and basins. Over time, these depressions fill with brine, forming the pools that we are exploring tonight. The first hint that these pools existed came from the instruments of oil and gas surveyors. They were mapping the seafloor with sonar, looking for structures that might indicate the presence of petroleum deposits, and their instruments kept picking up signals that they could not explain. Layers of water that seemed to reflect sound differently than the water around them. Layers that were denser, that had a different acoustic signature. At first, the surveyors thought their equipment was malfunctioning, but the signals kept appearing, again and again, always in the same places. And eventually, the oceanographers realized what they were seeing. They were seeing the surfaces of lakes of brine, sitting on the seafloor. The first proper exploration of a brine pool happened in the 1970s, when a team of scientists from Texas A&M University and the United States Geological Survey sent a submersible to investigate one of these anomalies. The submersible was the Johnson Sea Link, a small research vessel capable of diving to depths of up to 3,000 feet. The dive was scheduled to be a routine geological survey. No one expected to find anything remarkable. But as the submersible descended, the pilots saw something that made them stop. The seabed below them was changing. The usual brown ooze of the deep ocean floor was giving way to something pale and white, a kind of crust, like a frost that had settled on the bottom. And then, ahead of them, they saw the edge, a line in the sediment, as sharp as if it had been drawn with a ruler. On one side of the line, normal seafloor. On the other side, a basin filled with water that looked different, clearer, denser. And on the bottom of that basin, lying on the white crust, were the bodies of fish and crabs and shrimp, perfectly preserved, as if they had been arranged there by some unseen hand. The scientists in the submersible were the first human beings to lay eyes on a brine pool. And what they saw that day has been confirmed dozens of times since by expeditions to every ocean in the world. Brine pools are real. They are common, and they are deadly. But the most remarkable thing about them is not that they kill, it is what happens at their edges. Because at the edge of a brine pool, where the deadly salt water meets the normal ocean, something extraordinary is taking place. Something that may rewrite our understanding of life itself. Let us pause here for a moment. Let the image of that first discovery settle into your mind. A submersible, small and fragile, descending through the darkness. The floor of the sea, covered in white crust. The edge of the brine pool, sharp as a knife. And the bodies, lying in the salt, preserved in a stillness that has lasted for years. That is where we are going tonight. That is the world we are about to explore. Take another slow breath. Let the air fill your lungs and then release. Feel the weight of your body against your bed, the comfort of the blankets, the safety of your room. And know that somewhere far below, in the cold and the dark, the brine pools are waiting. They have always been waiting. And now we are going to visit them. We are going to descend into the Gulf of Mexico first, to explore the most famous and the most terrifying of all the brine pools. It has a name that sounds like something from a dark fairy tale. It is called the Jacuzzi of Despair. The Jacuzzi of Despair. Even the name sends a chill through you, does it not? It was discovered in 2014 by a team of scientists from Temple University, the University of Georgia, and the National Oceanic and Atmospheric Administration. They were exploring the seafloor of the Gulf of Mexico using a remotely operated vehicle called the Hercules, deployed from the exploration vessel Nautilus, when they came across something that none of them had ever seen before. It was a crater, a circular depression in the seafloor, about 30 meters across and 3 meters deep, and it was filled with brine. But not just any brine. This brine was hot, hotter than the surrounding water by a significant margin. The scientists checked their instruments. The temperature of the brine was 65 degrees Celsius. That is 150 degrees Fahrenheit, hot enough to cook a fish alive. And that is exactly what it did. The Jason's cameras showed the crater in perfect detail. The edges were rimmed with a white crust of salt, precipitated out of the brine as it met the colder seawater. The surface of the pool shimmered with heat. And inside the pool, lying on the bottom, were the bodies of deep-sea creatures that had made the fatal mistake of entering the hot brine. Crabs, fish, squid, all of them dead, all of them preserved in the salt. But the most haunting image was yet to come. As the Jason moved closer to the edge of the pool, its lights illuminated something that the scientists had not expected. A large fish, a species of deep-sea shark or ray, had swum directly into the hot brine. Its body was half submerged in the pool, the part that had entered the brine already cooked and preserved, the part that remained in the normal seawater still intact. The fish had died mid-stroke, its body frozen in the act of swimming. The scientists named it the Jacuzzi of Despair because of its hot, bubbling brine and the deadly effect it had on anything that entered. It was a dark joke, the kind of humor that deep-sea explorers use to cope with the strangeness of what they find. But the name stuck, and it perfectly captures the eerie, almost surreal nature of these underwater lakes. The Jacuzzi of Despair is not the only hot brine pool in the Gulf of Mexico. There are dozens of them, scattered across the seafloor, each one a little different in size and temperature and salinity. Some are small, barely a few meters across. Others are vast, stretching for hundreds of meters. Some are cold, their brine the same temperature as the surrounding water. Others are heated by geothermal activity, their brine bubbling up from the Earth's interior like a pot on a stove. But they all share the same basic structure: a depression in the seafloor, a pool of dense, salty brine, a sharp boundary between the brine and the normal seawater, and a ring of death around the edge where the creatures of the deep meet their end. The Gulf of Mexico is the perfect place for brine pools to form because of its unique geology. Beneath the seafloor of the Gulf lies a layer of salt that is more than a kilometer thick in some places. This salt was deposited over a period of about 10 million years during the Jurassic period, when the Gulf was a shallow, restricted basin that repeatedly evaporated. Each time the basin dried up, it left behind a layer of salt. Layer after layer, year after year, until the accumulation was staggering. Today, that salt is still moving. It is pushed upward by the pressure of the sediment above it, rising through cracks and faults in the seafloor. When it reaches the bottom of the ocean, it dissolves, creating the brine that feeds the pools. And because the salt is constantly being replenished from below, the pools never run dry. They have been there for thousands of years. They will be there for thousands more. The brine itself is a chemical cocktail unlike anything else on Earth. It is not just salt water. It is water that has been saturated with minerals from the salt deposits it has passed through. It contains high concentrations of sodium and chloride, of course, but also of calcium, magnesium, potassium, and sulfur. In some pools, the brine contains measurable amounts of rare metals like lithium, strontium, and barium. In the Red Sea brine pools, the concentration of precious metals is so high that scientists have seriously discussed the possibility of mining them. But it is the absence of something that makes brine pools deadly: oxygen. In the deep ocean, oxygen is scarce but present. Creatures have evolved to extract every possible molecule of it from the water they breathe. But in a brine pool, there is no oxygen at all. The brine is completely anoxic, and without oxygen, nothing that breathes can survive. When a fish swims into a brine pool, its gills are immediately overwhelmed. The salt draws water out of its cells, collapsing them. Its blood thickens, its organs fail. In a matter of seconds, the fish is dead. And because there is no oxygen in the brine, the bacteria that normally break down dead tissue cannot survive either. So the body does not decompose. It does not rot. It simply sits there, on the bottom of the pool, preserved for as long as the brine remains. This preservation is so perfect that some of the bodies found in brine pools look like they died yesterday. Their scales still have their color. Their eyes are still clear. Their internal organs are still intact. Scientists have pulled samples from brine pools and found that the tissue of the dead creatures contains intact DNA, preserved in the salt as if it had been placed in a freezer. This has led to an interesting theory among some researchers. If brine pools can preserve organic material so perfectly, could they also preserve evidence of ancient life? Could there be fossils, or even intact remains, of creatures that lived millions of years ago, sitting at the bottom of a brine pool somewhere, waiting to be discovered? It is a tantalizing possibility. The ocean floor is littered with the remains of ancient life, but most of it is destroyed by decay and scavenging before it can be fossilized. In a brine pool, however, the conditions are ideal for preservation. The lack of oxygen means no decay. The high salt content means no scavengers. The stillness of the water means no disturbance. A body that falls into a brine pool could remain there, effectively unchanged, for thousands or even millions of years. Scientists have already begun exploring this possibility. In 2015, a team of researchers from the University of Southern Mississippi analyzed the sediments at the bottom of several brine pools in the Gulf of Mexico. They found layers of organic material, including intact pollen grains and microscopic fossils, dating back thousands of years. The sediments were so well preserved that the scientists could reconstruct the climate history of the region by analyzing the pollen. They could tell what plants were growing on the nearby land at different times in the past. They could see the effects of ice ages and warm periods, all recorded in the layers of sediment at the bottom of a brine pool. This is the paradox of the brine pool. It is a place of death, but also a place of preservation. It kills, but it also remembers. The creatures that die in the brine do not simply vanish. They become part of the pool's history, its archive, its memory. And one day, when we learn how to read that archive, we may discover things about the past that we never knew. Let us stay with this image for a moment. The jacuzzi of despair, sitting at the bottom of the Gulf of Mexico. The hot brine shimmering in the light of a remotely operated vehicle. The bodies of fish and crabs and rays lying on the bottom, preserved like museum specimens. And beneath them, deeper in the sediment, layers of organic material that stretch back thousands of years. A history of life and death, written in salt. Now let us leave the Gulf of Mexico and travel to a very different place. We are going to cross the Atlantic Ocean, sail past the coast of Europe, and enter the Mediterranean Sea. Because the Mediterranean is home to some of the most spectacular brine pools ever discovered. The Mediterranean Sea is almost entirely enclosed by land. It is connected to the Atlantic Ocean only through the narrow Strait of Gibraltar. This means that the Mediterranean has a very different water cycle from the open ocean. It loses more water to evaporation than it gains from rainfall, so it is saltier than the Atlantic. And beneath its surface, it holds secrets that rival anything in the Gulf of Mexico. The Mediterranean brine pools were discovered in the 1970s during a series of oceanographic expeditions led by Russian and European scientists. They were mapping the seafloor of the eastern Mediterranean near the island of Crete when their instruments detected layers of water with unusually high salinity. They sent down sampling equipment and brought up water that was 10 times saltier than the surrounding sea. They had found the first Mediterranean brine pool. Since then, dozens of brine pools have been discovered in the Mediterranean. They are concentrated in the eastern basin, south of Greece and Turkey, in the deep waters of the Ionian Sea and the Levantine Sea. Some of them are enormous, covering areas of several square kilometers. Others are narrow and deep, like underwater canyons filled with brine. But the most remarkable thing about the Mediterranean brine pools is that they have rivers, actual rivers of brine, flowing along the seafloor. In 2013, a team of scientists from the University of Barcelona was exploring the seafloor of the eastern Mediterranean when they discovered something that seemed impossible. A river of water, flowing across the bottom of the ocean, with delta formations and levees and floodplains. The river was about 1 kilometer wide and nearly 10 meters deep at its center. It flowed for hundreds of kilometers along the seafloor, from a source somewhere in the deep basins of the Mediterranean to a terminus where it emptied into an even larger brine pool. The scientists named it the Brine River, and they were stunned by what they found. The Brine River is not made of normal water. It is made of brine, so dense and so salty that it does not mix with the seawater around it. It flows along the seafloor like a river of liquid glass, its surface shimmering with density currents. It has banks, where the normal ocean floor rises up to contain it. It has a current, which carries sediment and organic material along its length. It even has waves, ripples on its surface caused by the flow of the brine, and along its banks, just like along the edges of the brine pools, there is life. Microbial mats, thick, layered communities of bacteria that thrive on the chemical gradient between the brine and the normal seawater. These mats are alive. They are active. They are the only things that can survive at the edge of the Brine River. The discovery of the Brine River changed the way scientists think about brine pools. It showed that brine is not just sitting still, collecting in depressions. It can flow. It can move across the seafloor, carving channels and building deltas, just like a river on land. It can shape the landscape of the deep ocean in ways that we are only beginning to understand. And it raises a fascinating question. If there are rivers of brine on the seafloor, could there be other features too? Waterfalls, lakes, oceans within the ocean? The answer appears to be yes. In the Mediterranean, scientists have found evidence of brine cascades, where brine flows over the edge of underwater cliffs and falls into deeper basins, creating underwater waterfalls of salt water. They have found brine lakes that are so deep and so isolated that the water at the bottom has not mixed with the surrounding ocean for tens of thousands of years. They have found brine pools that contain different layers, like a cake, each layer with a different salinity and temperature and chemical composition. The more we explore, the more we realize that the deep ocean is not a single uniform body of water. It is a mosaic, a patchwork of different environments, each with its own chemistry and physics and biology. And brine pools are one of the most extreme and dramatic examples of this diversity. But the Mediterranean brine pools have another secret, one that is even more surprising. They are not just dead zones, they are oases. When scientists explored these brine pools, they discovered something that contradicted everything they knew about these environments. They found life. Not microbial life, although that was present too, but actual, visible, multicellular life. Creatures that were living in the brine. At first, the scientists thought their instruments were malfunctioning. They had sampled the water from a brine pool in the Latalante basin of the eastern Mediterranean, expecting to find nothing but salt and dead organic matter. But when they examined the sample under a microscope, they saw something moving. Tiny creatures, barely visible to the naked eye, swimming in the brine. They were a type of multicellular organism called a loricifera, a microscopic animal that lives in the spaces between sediment grains on the seafloor. And they were alive. They were thriving, in water that was over 8 times saltier than the normal ocean. This discovery was published in 2010 in the journal BMC Biology, and it caused a sensation. Until that moment, the scientific consensus was that nothing larger than a bacterium could survive in brine pools. The salinity was simply too high, the lack of oxygen too extreme. But here was proof that complex life could adapt to even the most hostile conditions. Since then, other organisms have been found living in and around brine pools. Nematodes, tiny worms, single-celled protists, and in the margins of the pools, where the brine mixes with normal seawater, entire communities of organisms have been found. Mussels, tube worms, bacterial mats that cover the seafloor like living carpets. These communities are not just surviving, they are thriving. They grow faster and denser than the communities in the surrounding deep ocean. They are like cities in the desert, clustered around the edge of the deadly lake, drawing energy from the chemical gradient between the brine and the seawater. The reason for this abundance is the chemistry of the brine. When the supersaline water meets the normal seawater, it creates a reaction. Minerals precipitate out of the solution, forming solid particles that float in the water like microscopic snowflakes. These particles are rich in carbon and other nutrients, and the organisms that live at the edge of the pool feed on them. They have adapted to exploit the very phenomenon that kills everything else. This is one of the great lessons of the deep ocean. Life finds a way. Even in the most hostile places, the places that seem designed to destroy life, organisms can adapt and thrive. The brine pools kill, yes, but they also nourish. They are places of death and life, intertwined in a way that we are only beginning to understand. Let us pause now. Let the strangeness of this sink in. Lakes at the bottom of the sea, rivers of salt water, dead fish preserved like statues, and at the edges of it all, life. Tiny creatures, swimming in the poison, living where nothing should be able to live. We are only halfway through our journey. There is much more to explore. But before we go further, take a moment. Breathe. Let your mind drift with the currents of the deep. Let the images settle. We are going to the Red Sea next, to the hottest, deepest, richest brine pools on Earth. And what we find there may change everything. The Red Sea is one of the most unusual bodies of water on Earth. It is long and narrow, stretching for over 2,000 kilometers between Africa and the Arabian Peninsula. It is shallow at its northern end, where it connects to the Mediterranean through the Suez Canal, but it deepens dramatically in the south, reaching depths of over 2.5 kilometers. And beneath its surface, hidden in its deepest basins, lie some of the most extreme brine pools ever discovered. The Red Sea brine pools were first detected in the 1960s during a series of oceanographic surveys conducted by research vessels from the United States, Germany, and the Soviet Union. The scientists were studying the geology of the Red Sea, which is one of the most tectonically active regions on Earth. The African and Arabian plates are pulling apart, creating a rift valley that runs the length of the sea. This rift is a place where new oceanic crust is being formed, where magma rises from the mantle and cools into solid rock. And where the crust is thin and fractured, seawater can seep down, get heated by the magma, and rise again as superheated brine. The first hint of something unusual came from temperature measurements. The research vessels were lowering instruments into the deep basins of the Red Sea, and their thermometers were recording temperatures that made no sense. At depths where the water should have been near freezing, the instruments were showing temperatures of over 40 degrees Celsius. Over 100 degrees Fahrenheit. The scientists thought their equipment was broken. But when they replaced the thermometers and tried again, they got the same readings. They sent down sampling bottles and brought up water that was thick and oily, with a smell of sulfur and metal. When they analyzed it, they found that it was nearly 8 times saltier than normal seawater, and it was rich in dissolved metals: iron, zinc, copper, lead, silver, gold. The brine that the scientists had sampled was literally a liquid ore, a solution of precious metals that would be worth billions of dollars if it could be mined. The discovery caused a rush of scientific interest. Expeditions were launched to map the Red Sea brine pools in detail. What they found was a system of deep, isolated basins, each one filled with brine at a different temperature and chemical composition. The largest and most famous of these is the Atlantis II Deep. The Atlantis II Deep is a basin about 15 kilometers long and 5 kilometers wide, located at a depth of over 2 kilometers in the central Red Sea. It is filled with brine that is heated to temperatures of up to 68 degrees Celsius. The brine is stratified, meaning it is divided into distinct layers, each with different temperatures and salinities. The upper layer is the coolest and least salty. The lower layer is the hottest and most concentrated, with a salinity that is over 7 times that of normal seawater. The amount of metal dissolved in the Atlantis II Deep is staggering. Scientists estimate that the brine contains over 90 million tons of zinc, 500,000 tons of copper, and significant amounts of silver and gold. The total value of the metals in the Atlantis II Deep has been estimated at over $2 billion. And this has led to a long-running debate about whether the brine pools should be mined. On one side of the debate are those who see the brine pools as a resource. The metals are there, concentrated in the brine, waiting to be extracted. The technology exists to pump the brine to the surface and process it, and the potential profits are enormous. Proponents argue that mining the Red Sea brine pools could provide a source of rare metals that would reduce our dependence on land-based mining, which is often environmentally destructive. On the other side are those who argue that the brine pools are a unique scientific resource. They are natural laboratories, places where we can study the processes that create ore deposits, the chemistry of extreme environments, and the limits of life. Mining them would destroy them. It would disrupt the delicate chemical balance of the pools, mix the layers, and potentially release toxic metals into the surrounding ocean. And once the pools were disturbed, the scientific information they contain would be lost forever. So far, the scientists have won the argument. The Red Sea brine pools are protected by international agreements, and mining has not been permitted. But the debate is not over. As the demand for rare metals increases, the pressure to exploit the brine pools will grow. And one day, we may have to decide whether the knowledge they contain is worth more than the metals they hold. But the metals are not the only remarkable thing about the Red Sea brine pools. There is something else, something even more profound, something that has to do with the origins of life. The Red Sea brine pools are among the most extreme environments on Earth. High temperature, high pressure, high salinity, no oxygen, high concentrations of toxic metals. By every measure, they should be completely sterile. And yet, when scientists have sampled the brine from the Atlantis too deep, they have found life, not the microbial mats that thrive at the edges of the Gulf of Mexico pools, not the loricifera that live in the Mediterranean brine. Actual living bacteria swimming in the hot, toxic, metal-rich brine of the Red Sea. They are extremophiles, organisms that have adapted to conditions that would kill any other form of life. They are called halophiles, or salt-loving organisms, and they represent some of the most ancient forms of life on Earth. The bacteria found in the Red Sea brine pools are not just surviving. They are active. They are metabolizing. They are reproducing. They are using the chemical energy in the brine to fuel their existence, in a process that is completely independent of the sun. They are chemosynthetic, meaning they derive their energy from chemical reactions rather than from photosynthesis, and this has profound implications for our understanding of where and how life can exist. If life can thrive in the hot, salty, metal-rich brine of the Red Sea, could it also thrive in similar environments on other planets? On Mars, where there is evidence of ancient salt deposits? On Europa, one of Jupiter's moons, where a subsurface ocean of liquid water is thought to exist beneath a thick layer of ice? On Enceladus, a moon of Saturn, where geysers of water vapor have been detected, suggesting the presence of liquid water and chemical energy? The answer increasingly appears to be yes. The extremophiles of the Red Sea brine pools are living proof that life can adapt to environments that we once thought were impossible. They expand our understanding of the habitable zone, the range of conditions under which life can exist. And they give us hope that if life can survive in a brine pool at the bottom of the Red Sea, it might also survive in the oceans of distant worlds. But there is another reason why the Red Sea brine pools are important to our understanding of life. They may offer a glimpse into the conditions under which life first arose on Earth. The early Earth was a very different place from the world we know today. The atmosphere was nearly devoid of oxygen. The oceans were hot and acidic. The land was barren and volcanic, and the seas were filled with dissolved minerals and metals, leached from the rocks by the constant rain and the volcanic activity. In other words, the early Earth was a lot like a brine pool. This has led to the theory that life may have originated in environments similar to brine pools. The high concentrations of dissolved minerals would have provided the raw materials for the formation of organic molecules. The chemical energy released by the mixing of hot and cold water, of acidic and alkaline fluids, would have provided the energy source for the first metabolic reactions. And the protective environment of the pool, isolated from the hostile conditions of the early ocean, would have provided a safe haven where the first cells could develop. This theory is known as the brine pool hypothesis for the origin of life. It is not as famous as the hydrothermal vent theory, which proposes that life began at the superheated vents on the ocean floor. But it is gaining support as we learn more about the chemistry of brine pools and the organisms that live in them. The key to the theory is the concept of chemical gradients. At the edge of a brine pool, where the dense brine meets the normal seawater, there is a sharp gradient in salinity, temperature, and chemical composition. This gradient is a source of energy, and the organisms that live at the edge of the pool exploit it. They use the energy released by the mixing of the two waters to drive their metabolism. Now imagine the same process happening on the early Earth. Imagine a brine pool, formed by the evaporation of seawater in a shallow basin, sitting at the bottom of the primordial ocean. The pool is rich in dissolved minerals and metals. The water around it is rich in carbon dioxide and other gases. Where the two meet, at the interface between the brine and the seawater, chemical reactions are constantly occurring. Some of those reactions produce organic molecules, amino acids, nucleotides, the building blocks of life. Over time, those organic molecules accumulate at the interface. They interact with each other, forming longer chains. They become encapsulated in tiny bubbles of lipid membranes, formed from the fatty acids that were also present in the brine. And eventually, somewhere in the gradient between life and non-life, the first living cells emerged. This is not a proven theory. It is a hypothesis, a speculation, a story that scientists are still trying to piece together. But it is a compelling one. And it is supported by the conditions we find in brine pools today. The Red Sea brine pools are particularly interesting in this context because they are hot. The heat provides energy for chemical reactions, speeding up the processes that could lead to the formation of organic molecules. The high pressure caused by the depth of the pools also affects the chemistry, allowing reactions to occur that would not be possible at the surface. And the high concentrations of metals provide catalysts, substances that facilitate chemical reactions without being consumed themselves. In a very real sense, the Red Sea brine pools may be time machines. They may preserve in their chemistry and biology a record of the conditions under which life first appeared on our planet, and by studying them, we may be able to understand the greatest mystery of all, how life began. Let us stay with this thought for a moment. The idea that the same deadly lakes that kill fish and preserve their bodies may also be the places where life first emerged. That the very conditions that make brine pools so hostile to modern life may have been the conditions that gave birth to life itself. There is a deep poetry in this. A circle, a balance. Death and life, intertwined in the same salt water, separated by billions of years of evolution. Take a slow breath. Let the weight of that idea settle into your mind. The brine pools are not just death traps. They are also museums of the ancient Earth. They are windows into the deep past, and they are laboratories where we can watch the processes of life unfolding in real time. We are going to leave the Red Sea now and travel to another ocean, but before we go, let us remember what we have seen, the hot, shimmering surface of the Atlantis too deep. The layers of brine, each one different, each one a separate world. The bacteria, swimming in the poison, living where nothing should live, and the metals, dissolved in the water, waiting for someone to claim them. The Red Sea brine pools are a reminder that the ocean is not a single place. It is many places, layered on top of each other, hidden from our view. And the deeper we go, the stranger they become. Now let us go to the Southern Ocean, to the waters around Antarctica. Because there, in the coldest, most remote part of the world, there are brine pools that are different from anything we have seen so far. They are called cryogenic brine pools, and they form in a completely different way. The Southern Ocean surrounding Antarctica is the most remote and unforgiving body of water on Earth. It is cold beyond anything most of us can imagine. The surface temperature hovers near the freezing point of seawater, around -2 degrees Celsius. The winds are relentless. The waves are enormous. And beneath the surface, in the darkness of the deep, the cold is absolute. But even here, in this frozen world, brine pools exist. They are called cryogenic brine pools because they are formed by the freezing of seawater rather than by the dissolution of salt deposits. And they are a phenomenon that is still not fully understood. When seawater freezes, the ice that forms is mostly pure water. The salt is excluded from the crystal structure of the ice. It is pushed out, concentrated into pockets of dense, cold, extremely salty water that sinks down through the ice and accumulates beneath it. This process is called brine rejection. and it is one of the most important mechanisms driving ocean circulation in the polar regions. As the brine sinks, it flows down the continental slope of Antarctica, carving channels in the seafloor as it goes. These channels can be hundreds of kilometers long and tens of meters deep. They are like underwater riverbeds carved by the flow of cold, dense brine. And at the bottom of these channels, in depressions on the seafloor, the brine collects and forms pools. The cryogenic brine pools of Antarctica are different from the ones we have seen in the Gulf of Mexico and the Red Sea in several important ways. First, they are cold. Not just cold compared to the Red Sea pools, but cold compared to the surrounding water. The brine in these pools is at or below the freezing point of normal seawater. It is supercooled, meaning it is liquid at a temperature that would normally cause it to freeze, but the high salt content keeps it from solidifying. Second, they are dynamic. The cryogenic brine pools are not static bodies of water. They are constantly being fed by new brine, created as seawater freezes at the surface. The brine flows down through channels in the ice shelf, cascading into the pools below. This creates currents and mixing, keeping the pools active and changing. And third, they are alive. Despite the extreme cold and the high salinity, the cryogenic brine pools of Antarctica are teeming with life. Not just bacteria, but larger organisms, sea stars, worms, crustaceans. Even fish have been found living in and around the brine pools. How do they survive? The high salt content of the brine depresses its freezing point, meaning it remains liquid at temperatures that would freeze normal seawater. This creates a refuge, a liquid oasis in a frozen world. The organisms that live in the brine pools have adapted to the cold and the salt, evolving proteins and membranes that function in conditions that would kill most other life forms. One of the most remarkable discoveries in the Antarctic brine pools occurred in 2010, when a team of scientists from the British Antarctic Survey and the University of Bristol were exploring the seafloor beneath the Larsen ice shelf. They had drilled through nearly 300 meters of ice to reach the water below, and they were lowering instruments into the dark, cold sea. When they measured the salinity of the water near the seafloor, they found something unexpected. The water was nearly twice as salty as normal seawater. They had discovered a cryogenic brine pool. The scientists sent down a camera to see what was living there. The images that came back were stunning. The seafloor around the brine pool was covered in a thick carpet of microbial mats, which looked like a white and orange fuzz stretching across the sediment. Clams were buried in the sediment, their siphons sticking up like tiny snorkels. Worms wriggled through the mats, and at the very edge of the brine pool, where the brine met the normal seawater, there were fields of sea anemones, their tentacles waving in the current. This was life in one of the most extreme environments on Earth, underneath hundreds of meters of ice, in water that was so salty it should have been uninhabitable, and yet there it was, thriving. The discovery of life in Antarctic brine pools has important implications. It suggests that even in the most extreme environments, life can find a way. It expands our understanding of the limits of life, of the range of conditions under which organisms can survive. And it has particular relevance for the search for life beyond Earth. Consider Europa, one of Jupiter's moons. Europa is covered in a thick layer of ice, beneath which there is thought to be a global ocean of liquid water. The ocean is kept liquid by tidal heating, the gravitational pull of Jupiter causing the moon to flex and generate heat. But the surface of Europa is exposed to the vacuum of space, and it is bombarded by radiation. Any life that exists in Europa's ocean would have to survive in conditions that are very similar to the Antarctic brine pools. And then there is Enceladus, a moon of Saturn. Enceladus has geysers that shoot plumes of water vapor and ice particles into space. The water is salty, it contains organic molecules, and it is warm, heated by the same tidal forces that keep Europa's ocean liquid. If there is life in Enceladus's ocean, it might be similar to the organisms that live in the Antarctic brine pools. Studying these pools, then, is not just about understanding our own planet. It is about preparing for the discovery of life on others. It is about learning to recognize the signatures of life in extreme environments, so that when we send probes to Europa or Enceladus, we know what to look for. But the Antarctic brine pools have another secret, one that is perhaps even more important. They are also sites of intense biological and chemical activity that may be affecting the global climate. The seafloor around Antarctica is rich in methane. Methane is a greenhouse gas, much more potent than carbon dioxide. It is locked up in the sediment in the form of methane hydrates, ice-like structures that contain methane molecules trapped inside a lattice of water molecules. These hydrates are stable under the cold temperatures and high pressures of the deep ocean. But if the temperature rises or the pressure decreases, the hydrates can destabilize, releasing methane into the water and potentially into the atmosphere. In the cryogenic brine pools, scientists have found evidence that the brine is causing the methane hydrates to destabilize. The high salt content of the brine interferes with the chemical bonds that hold the hydrates together, causing them to break down and release methane. This methane then bubbles up through the water column, potentially reaching the surface and entering the atmosphere. The amount of methane locked up in the seafloor around Antarctica is enormous. Some estimates suggest that there is more carbon stored in methane hydrates than in all the fossil fuel deposits on Earth combined. If even a small fraction of that methane were released, it could have a significant impact on global climate. The discovery that brine pools can destabilize methane hydrates adds a new layer of complexity to our understanding of the Earth's climate system. It suggests that the polar regions are not just passive victims of climate change. They are active participants, with feedback loops and tipping points that we are only beginning to understand. Let us take a moment here. Let the cold of the Antarctic sink into your awareness. The ice above, the dark water below, the brine pool sitting at the bottom of the sea, slowly releasing methane into the ocean. The microbial mats, living on the edge of the pool, doing their quiet work. The sea anemones, waving their tentacles in the cold brine. This is a world that most humans will never see, a world that exists on the edge of possibility, a world that is changing, even as we speak. We have now visited brine pools in 3 different oceans. We have seen hot pools and cold pools. We have seen pools that kill and pools that nurture. We have seen the bodies of the dead and the living communities that surround them. But there is one more type of brine pool that we have not yet explored. And it may be the strangest of all. We are going to the Mediterranean again, but not to the brine rivers and lakes of the Eastern Basin. We are going to the Western Mediterranean, to a place called the Gulf of Cadiz. And there, we are going to find something that looks like it belongs on another planet. The Gulf of Cadiz lies off the coast of Spain and Portugal, at the entrance to the Mediterranean Sea. It is a region of complex geology, where the African and Eurasian plates are colliding, creating underwater mountains, deep trenches, and fields of mud volcanoes. And buried beneath the sediment of the Gulf of Cadiz, there are vast deposits of salt, left over from the Messinian salinity crisis. This is a story that deserves its own moment. The Messinian salinity crisis was an event that occurred about 6 million years ago, when the Strait of Gibraltar closed, cutting off the Mediterranean Sea from the Atlantic Ocean. With no inflow of fresh seawater, the Mediterranean began to evaporate. Over a period of about 700,000 years, the sea level dropped by over a kilometer, and the Mediterranean became a series of shallow, hypersaline lakes. The salt that was deposited during this time is enormous in volume. It is estimated that over 1 million cubic kilometers of salt were laid down on the floor of the Mediterranean. When the Strait of Gibraltar finally reopened, the Atlantic rushed back in, refilling the Mediterranean in what geologists believe was a catastrophic flood of immense proportions. But the salt deposits remained, buried beneath the new sediment. And today, those deposits are still influencing the chemistry of the Mediterranean Sea. In the Gulf of Cadiz, the salt deposits are close to the surface, and they interact with the seawater in complex ways. Seawater seeps down through the sediment, dissolves the salt, and rises again as brine. The brine flows along the seafloor, forming pools and rivers and lakes, and in some places it erupts from the sediment in the form of brine volcanoes. Brine volcanoes are exactly what they sound like. They are mounds of sediment, formed by the eruption of brine from below. The brine carries sediment with it, building up a cone-shaped structure on the seafloor. From the top of the cone, brine flows out like lava, cascading down the sides and pooling at the base. The brine is dense and heavy, so it does not rise and disperse like a normal volcanic plume. It flows downhill, following the contours of the seafloor, creating rivers of salt water that stretch for kilometers. The Gulf of Cadiz has hundreds of these brine volcanoes, ranging in size from small bumps on the seafloor to massive structures hundreds of meters high. Some of them are active, constantly spewing brine and sediment. Others are dormant, their vents sealed by salt and mineral deposits. Together, they form a landscape that is unlike anything else on Earth. A landscape shaped by the flow of salt water, where rivers and lakes and volcanoes are all made of brine. And on this strange landscape, life has found a way. The mud volcanoes of the Gulf of Cadiz are home to some of the most diverse and abundant communities of deep-sea organisms ever discovered. The brine that seeps from the volcanoes is rich in methane and other hydrocarbons, which provide energy for chemosynthetic bacteria. These bacteria form the base of a food chain that includes tube worms, mussels, clams, crabs, and fish. In 2002, a team of scientists from the Spanish Institute of Oceanography explored one of the largest mud volcanoes in the Gulf of Cadiz, a structure called the Captain Arutyunov mud volcano. They sent down a remotely operated vehicle to survey the volcano, and the images they received were astonishing. The slopes of the volcano were covered in a dense carpet of living organisms. White tube worms, up to a meter long, extended from the sediment like a forest of pale trees. Mussels clustered around the vents, their shells coated in a layer of orange and white bacteria. Crabs crawled through the fields of tube worms, feeding on the detritus. And at the base of the volcano, where the brine pooled in depressions on the seafloor, there were fields of sea cucumbers, their bodies pale and translucent, feeding on the organic matter that settled from above. This was life in the midst of a brine field. Life that had adapted to the high salinity, the lack of oxygen, and the presence of toxic chemicals. Life that was thriving in conditions that should have been uninhabitable. The discovery of the Gulf of Cadiz mud volcanoes changed the way scientists think about brine environments. It showed that brine seeps, far from being dead zones, can be centers of biological activity. They are oases in the deep ocean, supporting communities of organisms that are as rich and diverse as any on Earth. The reason for this abundance is the same as in the other brine pools we have explored. The boundary between the brine and the normal seawater creates a chemical gradient, and that gradient is a source of energy. Organisms that can exploit that energy thrive. And in the Gulf of Cadiz, the gradient is particularly strong because the brine is so rich in methane and other hydrocarbons. But the Gulf of Cadiz has another secret, one that is only now being understood. Beneath the sediment, in the deep layers of salt, there may be vast reservoirs of liquid brine, isolated from the surface for millions of years. These reservoirs are the source of the brine that feeds the mud volcanoes and the brine pools, and they may contain something extraordinary: ancient water. Water that has been trapped beneath the seafloor for millions of years, unchanged since the time of the Messinian salinity crisis. In 2019, a team of scientists from the University of Barcelona and the Spanish National Research Council drilled into one of these salt deposits, extracting samples of the brine from deep beneath the seafloor. When they analyzed the samples, they found that the water was indeed ancient. It was over 5 million years old, and it contained organic molecules that had been preserved in the salt for all that time. The scientists also found something else. They found living bacteria in the ancient brine, bacteria that had been trapped in the salt deposits for millions of years, surviving in a state of suspended animation, waiting for the conditions to become favorable for growth again. This discovery was published in the journal Science in 2020, and it was met with both excitement and skepticism. Some scientists argued that the bacteria were contaminants introduced during the drilling process, but others pointed out that the bacteria were found at concentrations that suggested they had been there for a long time, and that they were adapted to the high salinity and pressure of the deep brine. If the discovery is confirmed, it would mean that life can survive in brine for millions of years. It would mean that the salt deposits beneath the seafloor are a vast reservoir of living organisms waiting to be revived. And it would mean that the brine pools on the seafloor are not just isolated features. They are the surface expression of a deep biosphere, a world of life that extends kilometers beneath the seabed. This is a humbling thought. We have been exploring the ocean for centuries, but we have barely scratched the surface. Beneath the seafloor, in the dark and the salt and the pressure, there may be an entire world of life that we have never seen, a world that is older than anything on the surface. A world that has been waiting patiently for us to discover it. Let us pause now. Let the image of that deep biosphere settle into your mind. The salt deposits, stretching for kilometers beneath the seafloor. The ancient brine, trapped in the pores of the salt. The bacteria, sleeping in the darkness, waiting for 1,000,000 years. And above them, on the seafloor, the brine pools and the mud volcanoes, the rivers of salt and the lakes of death. We are connected to this hidden world. The water that flows through the brine pools is the same water that flowed through the oceans millions of years ago. The salt that kills the fish is the same salt that preserves the bacteria, and the life that thrives at the edge of the pools is the same life that may have emerged in the primordial seas. The brine pools are not just curiosities, they are threads connecting us to the deep history of the Earth, and every time we explore one, we pull on that thread, unraveling a little more of the story of our planet. We are going to leave the Gulf of Cadiz now and travel to the one place where brine pools have been found that may contain the most important secret of all. We are going to the bottom of the Mediterranean Sea, to the deepest brine pools ever discovered. And we are going to find out what is hiding in the darkness at the very bottom of the sea. The deepest brine pools in the Mediterranean are found in the Eastern Basin, south of Greece and Crete, in a region called the Hellenic Trench. This is one of the most tectonically active areas in the Mediterranean, where the African plate is diving beneath the Eurasian plate, creating deep trenches and volcanic arcs. And in the deepest parts of these trenches, at depths of over 4,000 meters, the brine pools are found. These are the ultra-deep basins of the Eastern Mediterranean, such as the Discovery Basin and the Tyro Basin. They are among the deepest and most isolated brine pools ever found, and they are also among the oldest. The brine in these deep basins has been accumulating for over 100,000 years. During that time, it has been completely isolated from the surrounding ocean. The water at the bottom of these pools has not been in contact with the atmosphere or with any living organism for tens of thousands of years. It is a time capsule, sealed at the bottom of the sea. The conditions in these pools are extreme. The salinity is over 8 times that of normal seawater. The temperature is around 14 degrees Celsius, warm compared to the near-freezing water around it. There is no oxygen, and the pressure is immense, over 400 times the pressure at the surface. When scientists first sampled these pools, they expected to find nothing but sterile brine. Instead, they found a thriving microbial community, bacteria and archaea living in the brine, using chemical reactions to sustain themselves. These organisms are not just surviving. They are active, reproducing, evolving. They are the most extreme salt-tolerant organisms ever discovered. But it was what they found in the sediment beneath the brine that was truly remarkable. Because the anoxic conditions of the brine pool had preserved the sediment in exquisite detail. Each layer of sediment represented a different period in Earth's history. And within those layers, the scientists found fossils, microscopic fossils, the remains of tiny organisms that had lived and died in the Mediterranean over the past 100,000 years. Because the brine pool had preserved them so perfectly, the scientists could study the fossils in detail. They could see the structure of the organisms, the shape of their shells, the composition of their tissues. They could reconstruct the ecological history of the Mediterranean, seeing how the populations of different species had changed over time in response to climate shifts and sea level changes. This is the power of brine pools as scientific tools. They are not just objects of study themselves. They are archives. They preserve the history of the ocean in their sediments, layer by layer, for thousands of years. And by reading those layers, we can learn about the past. But the preservation power of brine pools extends beyond microscopic fossils. In the right conditions, they can preserve larger objects as well. And this has led to one of the most fascinating and controversial theories about brine pools. There is a theory proposed by some marine archaeologists that brine pools may contain perfectly preserved shipwrecks. The idea is simple. If a ship sinks in an area where a brine pool exists, and if the ship settles into the brine, it could be preserved for thousands of years. The lack of oxygen would prevent wood from rotting. The high salt content would prevent organisms from boring into the wood. The stillness of the water would prevent the wreck from being disturbed. The ship could remain intact, exactly as it sank, for millennia. And if the theory is correct, the implications are staggering. There could be ships from ancient civilizations, from the Greeks and Romans and Phoenicians, preserved at the bottom of the Mediterranean, inside a brine pool. Ships that sailed the seas thousands of years ago, carrying cargo and passengers and secrets, now sitting at the bottom of the ocean, perfectly intact, waiting to be discovered. Is this just fantasy? Perhaps. But there are reasons to take it seriously. In the Black Sea, a body of water that has a similar anoxic layer, scientists have discovered perfectly preserved shipwrecks dating back over 2,000 years. In 2016, a team of marine archaeologists from the University of Southampton discovered over 40 shipwrecks in the Black Sea, some of them so well preserved that the ropes and rigging were still intact. The oldest of these wrecks was over 2,000 years old, from the Greek and Roman periods. It looked almost new, as if it had sunk only a few years ago. The Black Sea is not a brine pool, but it has a similar chemistry. The lower layers of the Black Sea are anoxic, containing no oxygen because the water is stratified. The result is the same. Shipwrecks are preserved in the Black Sea at a level of detail that is impossible in other oceans. And if it happens in the Black Sea, it could also happen in a brine pool. In fact, there is already evidence that brine pools can preserve large objects. In the Gulf of Mexico, in one of the brine pools discovered by the oil and gas surveyors, there is a shipwreck. It is a wooden ship, probably from the 19th or early 20th century, that sank near a salt dome. The wreck lies partially buried in sediment, and the parts of it that are exposed to the brine are remarkably well preserved. The wood is still intact, the nails are still in place, the shape of the hull is still visible. The ship has not been formally studied. It is in deep water, in a location that is difficult to access, and it is not considered a priority for archaeological research. But it is proof of the concept. Brine pools can preserve shipwrecks, and if they can preserve ships from the 19th century, they could preserve ships from older periods as well. The Mediterranean is full of shipwrecks, from thousands of years of maritime history. Many of them are in deep water, beyond the reach of divers. Some of them may be sitting at the bottom of brine pools, preserved for us to discover. But the theory goes even further. Some researchers have speculated that brine pools could preserve more than ships. They could preserve human remains, and not just remains, but bodies. Bodies that fell into the brine and were preserved, like the fish we saw in the jacuzzi of despair, because the conditions were exactly right for mummification. The idea is unsettling, but it is scientifically plausible. The brine that preserves the fish could also preserve a human body. The salt would dehydrate the tissues, preventing decay. The lack of oxygen would stop bacterial growth. The body would shrink and harden, but it would remain intact, its features recognizable for thousands of years. Has this happened? There is no evidence that it has, but the possibility exists, and the search for human remains in brine pools has become a topic of serious discussion among marine archaeologists and forensic scientists. Let us set aside that unsettling thought for a moment and return to the broader significance of brine pools. They are archives. They preserve the past, and they also, in a strange way, preserve the present. In the deepest brine pools, where the water has been isolated for thousands of years, the conditions have not changed. The temperature has not changed. The salinity has not changed. The chemistry has not changed. The pool is the same today as it was 10,000 years ago. This stability is rare in the natural world. Most environments change constantly in response to weather, seasons, climate, and the activity of living organisms. But a brine pool is different. It is a closed system. Nothing enters it and nothing leaves it, except by the slow diffusion of molecules across its boundaries. The pool is a world apart, a place outside of time. Scientists have studied the chemistry of these ancient brine pools to learn about the history of the ocean. By comparing the composition of the water in the pools to the composition of the modern ocean, they can see how the ocean has changed over thousands of years. They can measure the buildup of carbon dioxide from the atmosphere. They can track the changes in temperature and salinity caused by ice ages and warm periods. They can see the fingerprints of human activity, the chemical signatures of pollution and industry, reaching down even into these isolated depths. Because nothing escapes the brine pools, every change in the ocean above them is recorded, in some way, in the chemistry of the brine. The pools are like the rings of a tree, a record of the Earth's history written in salt. We have been descending for a long time. We have visited the Gulf of Mexico and the Red Sea, the Southern Ocean, and the Gulf of Cadiz, the deepest trenches of the Mediterranean. We have seen hot pools and cold pools, active pools and dormant pools, pools that kill and pools that nurture, and through it all, a picture has emerged. A picture of a world that exists alongside our own, hidden in the darkness of the deep. Brine pools are not just a curiosity. They are not just a scientific phenomenon. They are a reminder of how little we know about our own planet. They are a glimpse into a hidden world, a secret geography that exists beneath the familiar surface of the ocean. And they are a challenge to our understanding of life itself. If life can survive in the brine pools, what else is possible? If the conditions in the pools are similar to the conditions on early Earth, what do they tell us about our own origins? If the pools can preserve the past so perfectly, what secrets are they hiding? We are nearing the end of our journey, but before we ascend back to the surface, let us take one more dive. Let us go to the deepest brine pool ever discovered. A pool that exists at a depth of over 4,000 meters, in the darkest and most remote part of the ocean. A pool that may contain the answer to questions we have not yet asked. The deepest brine pool ever discovered is called the L'Atalante Basin. It is located in the eastern Mediterranean Sea, in the Hellenic Trench, at a depth of over 3,300 meters. It was discovered in 1993 by a team of French and Italian oceanographers who were mapping the seafloor of the Mediterranean as part of a geological survey. The L'Atalante Basin is a depression on the seafloor, several kilometers across, filled with brine. The brine in this basin is over 8 times saltier than normal seawater, and it is completely anoxic. The basin is so deep and so isolated that the water at the bottom has not mixed with the overlying ocean for tens of thousands of years. When the scientists first explored the L'Atalante Basin, they lowered a sediment core to the bottom. The core was a long tube designed to penetrate the sediment and bring up a sample of the seafloor. When the core was retrieved, the scientists found that the sediment at the bottom of the basin was completely undisturbed. There were no burrows from worms, no tracks from crabs, no signs of any life at all. The sediment was perfectly smooth, layered, and pristine. But it was what they found in the sediment that made the discovery truly remarkable. The sediment contained the remains of organisms that had lived in the Mediterranean thousands of years ago. Microscopic fossils, pollen grains, the shells of tiny plankton, all of them preserved in exquisite detail. Because the bottom of the L'Atalante Basin is completely anoxic, there is no decomposition. The organic material that falls into the basin is preserved exactly as it was when it sank. The scientists could see the individual cells of the microorganisms preserved in the sediment. They could see the delicate structures of the pollen grains. They could see the fine details of the plankton skeletons. And by analyzing these preserved remains, the scientists could reconstruct the history of the Mediterranean climate. They could see the shifts in temperature and rainfall that occurred over the past 100,000 years. They could see the effects of the ice ages and the warm periods. They could see the changes in vegetation and marine life that accompanied these shifts. The L'Atalante Basin is not just a brine pool. It is a library of the Earth's history, written in the language of salt and sediment. Since the discovery of the L'Atalante Basin, scientists have found similar deep brine pools in other parts of the Mediterranean. The Discovery Basin, the Tyro Basin, the Poseidon Basin. Each one is a separate library, a separate archive of the Earth's past, and each one has its own unique story to tell. But there is something else that makes the L'Atalante Basin and its neighboring pools special. They are not completely dead. We have already discussed the Loricifera, the tiny multicellular animals that were found living in the brine of the L'Atalante Basin. But there is more. At the interface between the brine and the normal seawater, where the two layers meet, there is a thin zone of mixing. This zone is only a few centimeters thick, but it is one of the most biologically active places in the deep ocean. The reason is the chemical gradient. Where the brine meets the seawater, there is a sharp change in salinity, temperature, and chemical composition. This gradient is a source of energy, and organisms have evolved to exploit it. Bacteria live at the interface, forming a dense microbial mat. They use the chemical energy from the gradient to fuel their metabolism. They are chemosynthetic, meaning they do not need sunlight to survive. They get their energy from the chemical reactions between the brine and the seawater. These bacteria form the base of a food chain. Tiny organisms graze on the bacteria. Larger organisms graze on them. And at the top of this miniature food chain are the loricifera, the microscopic animals that live in the brine itself. The loricifera are remarkable creatures. They are only about 1/4 of a millimeter long, barely visible to the naked eye. But they are complex animals with a nervous system, a digestive system, and a reproductive system. They are not simple bacteria. They are animals, and they live in water that is 8 times saltier than the ocean, with no oxygen, at a pressure that would crush a human being. When the discovery of the loricifera was announced in 2010, it made headlines around the world. It was the first time that complex multicellular life had been found living under completely anoxic conditions. It changed the way scientists think about the limits of life. Until that moment, it was believed that animals could not survive without oxygen. All animals, it was thought, needed oxygen to metabolize food, to generate energy, to live. But the loricifera proved that assumption wrong. They had evolved a way to live without oxygen, using a different metabolic pathway, one that did not require the gas that we breathe. How do they do it? The loricifera have organelles called hydrogenosomes, which are similar to mitochondria but do not require oxygen. They use hydrogen instead of oxygen to generate energy. It is a form of metabolism that is extremely rare in the animal kingdom, but it exists, and it allows the loricifera to survive in the anoxic brine of the L'Atalante Basin. The discovery of the loricifera has profound implications for the search for life beyond Earth. If complex animals can survive without oxygen, then the habitable zone for life expands dramatically. Planets and moons that were thought to be too hostile for life because they lack oxygen may actually be capable of supporting complex ecosystems. Europa, Jupiter's moon, has a subsurface ocean that is thought to be anoxic. Enceladus, Saturn's moon, also has a subsurface ocean that may be anoxic. If life can evolve without oxygen, these oceans could be teeming with organisms, perhaps even animals similar to the loricifera. But there is a deeper implication as well. The loricifera are not just survivors. They are a living link to the past. They represent a form of metabolism that may be very ancient, dating back to a time when the Earth's atmosphere had no oxygen, a time when the only life that existed was anaerobic, living in the dark, in the deep, in places like the brine pools. The loricifera may be living fossils, remnants of a world that existed before oxygen, before the rise of complex life, before the evolution of animals that breathe air. They are a window into the deep past of our own planet. Let us pause here. Let the significance of this sink in. In a brine pool at the bottom of the Mediterranean, there are animals that do not need oxygen to live. Animals that use a primitive form of metabolism that may be billions of years old. Animals that represent a living connection to the earliest forms of life on Earth. The brine pools are not just places of death. They are places of ancient life. They preserve the past in their sediments and in their waters. And they remind us that life is more adaptable, more resilient, and more surprising than we ever imagined. Take a slow breath. Let the idea of those tiny creatures swimming in the salt, living without oxygen, settle into your awareness. They are down there now as you lie here in the quiet of your room, going about their tiny lives in a world that is completely alien to our own. And they have been there for thousands of years, unchanged, unbothered, unnoticed. We are almost ready to ascend. But before we do, let us consider one more aspect of brine pools, an aspect that connects them to the deepest questions of all. The question of how life began on Earth, and whether it exists elsewhere in the universe. The brine pools, with their extreme conditions, their chemical gradients, and their isolated ecosystems, may be the closest we can get to recreating the conditions of the early Earth. They are natural laboratories where we can study the processes that may have led to the origin of life, and they are also natural testbeds where we can develop the techniques and technologies that we will need to search for life on other worlds. In the next part of our journey, we will explore the connection between brine pools and the origin of life. We will look at the chemistry of the pools, the reactions that occur at their interfaces, and the organisms that live there, and we will ask the question that drives all scientific inquiry. What does this tell us about who we are and where we came from. The origin of life is the greatest unanswered question in science. How did non-living matter, the simple molecules that existed on the early Earth, organize themselves into the first living cells? It is a question that has occupied the minds of scientists and philosophers for centuries, and we are still far from a definitive answer. But there are clues, and some of the most intriguing clues come from brine pools. The early Earth, as we have noted, was a very different place from the world we know today. The atmosphere was rich in carbon dioxide, methane, and ammonia. The oceans were hot and acidic. There was no oxygen, and the surface was bombarded by ultraviolet radiation from the sun because there was no ozone layer to block it. In these conditions, simple organic molecules could form. Experiments like the famous Miller-Urey experiment of 1952 showed that when you apply electrical sparks, simulating lightning, to a mixture of water, methane, ammonia, and hydrogen, you get amino acids, the building blocks of proteins, the components of life. But the Miller-Urey experiment produced only a small number of amino acids in low concentrations. And the real challenge for origin of life research is not just creating the building blocks of life. It is concentrating them, organizing them, and getting them to interact in the right way. This is where brine pools come in. Brine pools are natural concentrators. When seawater evaporates, the dissolved minerals become more concentrated. As the salinity increases, the chemical reactions between the dissolved molecules become more likely. The molecules are pushed closer together, increasing the chance that they will collide and react. In a brine pool, the concentration of dissolved organic molecules can be thousands of times higher than in the surrounding ocean. This creates a kind of chemical soup, where the ingredients for life are present in abundance. And at the edges of the pool, where the brine mixes with normal seawater, there are sharp chemical gradients. These gradients provide a source of energy, driving the reactions that could lead to the formation of more complex molecules. Imagine a brine pool on the early Earth. The pool is rich in organic molecules formed by the action of sunlight and lightning on the atmosphere. The molecules accumulate in the pool, concentrated by evaporation. At the same time, the pool is rich in minerals and metals, dissolved from the surrounding rocks. And at the interface between the brine and the seawater, where the two waters mix, there is a constant flow of energy. In this environment, it is possible that the first organic polymers formed, chains of amino acids, linked together into proteins, chains of nucleotides, linked together into RNA. These polymers are the essential machinery of life. Proteins do the work, catalyzing reactions and building structures. RNA stores information and carries instructions. How did these polymers form? In the modern world, they are formed by enzymes, the protein catalysts that drive the chemical reactions of life. But on the early Earth, there were no enzymes. The polymers had to form spontaneously, through non-biological processes. This is where the chemistry of brine pools becomes particularly interesting. The high salt concentration in brine has a powerful effect on the behavior of organic molecules. It can cause them to precipitate out of solution, forming concentrated layers on surfaces. It can encourage them to bond together, forming longer chains. It can protect them from degradation by excluding the water that would otherwise break them apart. In the laboratory, scientists have shown that amino acids can form short proteins, called peptides, in conditions similar to those found in brine pools. The high salt concentration, combined with the right temperature and pH, can drive the formation of peptide bonds, linking amino acids together. The reactions are slow, but they happen. And over millions of years, slow reactions can produce significant results. But it is not just proteins that can form in brine pools. The formation of RNA is also possible. RNA is a complex molecule, made up of a backbone of sugar and phosphate, with tags called bases attached to it. The bases are the letters of the genetic code. They store information in a sequence that can be copied and passed on. In a brine pool, the building blocks of RNA, called nucleotides, can accumulate and react. The high salt concentration can help them link together, forming chains of RNA, and the chemical energy from the gradients at the edge of the pool can drive the reactions forward. Scientists have been working for decades to create RNA in laboratory conditions that simulate the early Earth. They have made significant progress. They have shown that nucleotides can form spontaneously from simple starting materials. They have shown that nucleotides can link together into chains under the right conditions. And they have shown that some of these chains can act as catalysts, performing simple chemical reactions. But no one has yet created a self-replicating RNA molecule from scratch. That is the holy grail of origin of life research, a molecule that can make copies of itself. Because once you have a self-replicating molecule, you have the beginnings of evolution. You have heredity. You have the potential for life. Could a brine pool be the place where the first self-replicating molecule emerged? It is an intriguing possibility. The pool would provide the right chemical conditions, the right concentration of ingredients, and the right energy sources. And the isolation of the pool, separated from the surrounding ocean, would protect the fragile early stages of life from the hostile conditions of the early Earth. This is the brine pool hypothesis for the origin of life. It is not a proven theory. It is a speculation. But it is a speculation that is grounded in real chemistry and real biology. The next step in testing this hypothesis is to explore modern brine pools more thoroughly, looking for evidence of the chemical reactions that might have led to the origin of life. Scientists are doing this using advanced analytical techniques to study the organic chemistry of brine pools. They are finding complex organic molecules, including amino acids, sugars, and fatty acids. They are finding evidence of chemical reactions that could lead to the formation of polymers. And they are finding something else, something that may be more important than anything we have discussed so far. They are finding evidence of cells. In 2014, a team of scientists from the University of Southern Denmark and the University of Copenhagen published a paper in the journal Molecular Biology and Evolution, describing the discovery of large populations of bacteria living in the brine pools of the Mediterranean. The bacteria were not just surviving, they were thriving. And they were doing something that no one had expected. They were communicating. The bacteria in the brine pools were using chemical signals to coordinate their behavior. They were forming communities, working together, sharing resources. They were, in a very real sense, acting like a multicellular organism. This discovery was a surprise. Brine pools were thought to be too extreme for complex social behavior. But the bacteria had evolved a way to overcome the challenges of their environment by working together. They were a reminder that even in the most hostile places, cooperation can emerge. And if cooperation can emerge in a brine pool, could it also have emerged in the brine pools of the early Earth? Could the first cells have formed not as isolated individuals, but as communities of cooperating molecules? It is a beautiful idea. That life on Earth began not with a single spark, but with a community of molecules, working together, helping each other, sharing resources. A community that eventually became the first cell. Let us sit with this thought for a moment. The brine pools, the places of death and preservation, of salt and silence, may also be the places where life first took its first tentative steps, where the boundary between non-life and life was crossed, in a pool of salt water at the bottom of the primordial sea. We are almost at the surface now. The end of our journey is in sight. But before we emerge into the light, let us pause one last time. Let us let the darkness of the deep wrap around us. Let us feel the weight of the water above. Let us listen to the silence of the brine pools, the silence that has lasted for thousands of years. Because in that silence, there is knowledge. In that darkness, there is history. And in that salt, there is life. The organisms that live in brine pools are called extremophiles. They are organisms that have adapted to conditions that would be lethal to most life on Earth. And they are among the most fascinating creatures on the planet. Extremophiles are not rare. In fact, they are common in the deep ocean, living around hydrothermal vents, in cold seeps, and in the sediments of the seafloor. But the extremophiles of brine pools are special because they must cope with multiple extreme conditions at the same time. High salinity, high pressure, high temperature in some cases, low oxygen or no oxygen at all, and high concentrations of toxic metals. To survive in this combination of extremes, the organisms of brine pools have evolved remarkable adaptations. They have cell membranes that are reinforced to prevent the salt from drawing water out of their cells. They have proteins that are stabilized to prevent them from being denatured by the high salt. They have metabolic pathways that do not require oxygen, using sulfur, methane, or other chemicals instead. And they have enzymes that are unlike anything found in surface organisms. Enzymes that can function in high salt. Enzymes that can work under high pressure. enzymes that can catalyze reactions in the absence of oxygen. These enzymes are of great interest to biotechnology companies. They can be used in industrial processes that require extreme conditions. They can be used to clean up toxic waste, to produce biofuels, to synthesize pharmaceuticals. The extremophiles of brine pools are a resource, a library of biological tools that we are only beginning to explore. One of the most promising applications is in the field of bioremediation. Brine pool bacteria can break down toxic chemicals that would be resistant to other forms of treatment. They can metabolize heavy metals, converting them into less toxic forms. They can degrade hydrocarbons, cleaning up oil spills, and they can do this in environments where other organisms cannot survive. In 2018, a team of scientists from the University of California and the University of Texas published a study showing that bacteria from the Gulf of Mexico brine pools could degrade crude oil. The bacteria, which were collected from the edge of a brine pool near the site of the Deepwater Horizon oil spill, were found to be capable of breaking down the complex hydrocarbons in crude oil. They could use the oil as a food source, converting it into carbon dioxide and water. The discovery was significant because it suggested that brine pool bacteria could be used to clean up oil spills in the deep ocean. The bacteria are already adapted to the high pressure and low temperature of the deep sea. They are already equipped to deal with the toxic chemicals that are released during an oil spill, and they are already present in the environment, ready to do their work. But the study also raised a concern. If brine pool bacteria can degrade oil, what happens when a brine pool is contaminated by an oil spill? The Deepwater Horizon spill released millions of barrels of oil into the Gulf of Mexico, and some of that oil reached the seafloor. Did it contaminate the brine pools? Did it affect the delicate ecosystems at their edges? The answer is not clear. The brine pools are deep, and the oil may not have reached them in significant quantities, but the possibility is worrying. Brine pools are rare and fragile environments. They take thousands of years to form, and once they are disturbed, they may never recover. This brings us to a broader issue: the protection of brine pools. As we have explored in this journey, brine pools are scientifically valuable. They are archives of Earth's history. They are natural laboratories for studying the limits of life. They are sources of unique biological resources, and they are windows into the deep past of our planet. But they are also vulnerable. Deep-sea mining, oil and gas extraction, and bottom trawling all pose threats to brine pools. The mining of polymetallic nodules, which are found on the seafloor in many parts of the ocean, could disturb the sediment layers that contain the brine pools. The drilling for oil and gas could puncture the salt deposits that feed the pools, and the dragging of fishing nets across the seafloor could destroy the delicate microbial mats that live at the edges of the pools. International agreements exist to protect some deep-sea environments, but brine pools are not specifically protected. They are not mentioned in the United Nations Convention on the Law of the Sea. They are not included in the list of vulnerable marine ecosystems recognized by the Food and Agriculture Organization. And they are not covered by the International Seabed Authority's regulations for deep-sea mining. This is a gap in our protection of the ocean, and it is a gap that scientists are working to close. In 2019, a group of marine biologists and geologists published a paper in the journal Marine Policy, calling for the establishment of a global network of brine pool protected areas. They argued that brine pools are unique and irreplaceable environments, and that they deserve the same level of protection as coral reefs and hydrothermal vents. The proposal has not yet been adopted, but it is a start. It is a recognition that the brine pools are important and that they need to be preserved for future generations. Let us take a moment now to reflect on what we have learned. The brine pools are not just curiosities. They are not just scientific phenomena. They are part of the heritage of our planet. They contain information that is not available anywhere else. They preserve the history of the Earth's climate and ocean. They host unique organisms that have adapted to conditions found nowhere else. And they may hold clues to the origin of life itself. To lose a brine pool would be like burning a library. It would be to destroy a record of the Earth's past that can never be replaced. And it would be to eliminate a habitat for organisms that exist nowhere else. We have a responsibility to protect these places, not because they are useful to us, although they are, but because they are part of the natural world, because they are beautiful in their strangeness, because they are a reminder that the Earth is more complex, more surprising, and more wonderful than we can imagine. The brine pools have been there for thousands of years. They will be there for thousands more. if we let them. They sit in the darkness at the bottom of the sea, quietly preserving the past and supporting the present. They are part of the great system of the ocean, connected to everything else. And they are waiting for us to understand them, waiting for us to protect them, waiting for us to appreciate their strange, deadly beauty. But before we leave the brine pools behind, there is one more place we should visit. One more pool that has taught us more about these strange environments than perhaps any other. It is not the deepest pool. It is not the hottest pool. It is not the saltiest pool. But it is one of the most studied and one of the most revealing. It is called the Orca Basin. The Orca Basin is located in the Gulf of Mexico, about 300 kilometers south of the coast of Louisiana. It is a large, shallow depression on the seafloor, about 40 kilometers long and 20 kilometers wide, filled with brine. The brine in the Orca Basin is about 7 times saltier than normal seawater, and it is completely anoxic. The basin was discovered in the 1970s, during the same series of oil and gas surveys that led to the discovery of the first brine pools. But what makes the Orca Basin special is not its size or its salinity. It is what scientists have found at the interface between the brine and the normal seawater. Because at the Orca Basin, that interface is one of the most biologically productive places in the deep ocean. The interface between the brine and the seawater is a chemical gradient. At the top, normal seawater, rich in oxygen and nutrients. At the bottom, the brine, dense and salty and lifeless. And in between, a thin layer where the two waters mix, creating conditions that are ideal for certain kinds of bacteria. These bacteria are chemosynthetic. They use the chemical energy released by the mixing of the brine and the seawater to fuel their metabolism. They do not need sunlight. They do not need oxygen. They live in the gradient at the edge of the brine pool, and they thrive there. The bacteria in the Orca Basin are so abundant that they form a visible layer. A layer of living organisms floating at the interface between the brine and the seawater. The layer is only a few centimeters thick, but it stretches for kilometers across the surface of the basin. It is like a living skin covering the brine pool. Scientists have studied this layer extensively. They have sampled the bacteria and analyzed their DNA. They have measured their metabolic rates and studied their adaptations, and they have found something remarkable. The bacteria in the Orca Basin are not a single species. They are a community. Dozens of different species, living together, working together, sharing resources. Some of the bacteria are methanotrophs. They consume methane, using it as a source of carbon and energy. Others are sulfate reducers. They use sulfate instead of oxygen to break down organic matter. Others are autotrophs. They fix carbon dioxide, building organic molecules from the carbon in the water. Together, these bacteria form a complex ecosystem. They are the base of a food chain that includes larger organisms, worms, crustaceans, even fish, which swim through the interface layer, feeding on the bacteria and the tiny creatures that eat them. The Orca Basin is a reminder that even in the most extreme environments, life can be abundant. The bacteria at the interface of the brine pool are among the most productive organisms on Earth. They convert chemical energy into biomass at rates that rival the most productive ecosystems on the surface. And they do it in the dark, in the cold, under immense pressure, in water that would kill any other form of life. The Orca Basin has also taught us something else about brine pools. It has taught us about the role they play in the global carbon cycle. The organic matter that is produced by the bacteria at the interface of the brine pool does not stay there. Some of it sinks, falling into the brine itself. Because the brine is anoxic, the organic matter does not decompose. It accumulates at the bottom of the basin, layer after layer, year after year. Over time, this organic matter is buried by sediment. It becomes part of the geological record. And if the conditions are right, it can be transformed into oil or gas. This is the process that formed the petroleum deposits that we rely on today. The oil and gas that we burn for energy were once organic matter, produced by ancient organisms, preserved in anoxic environments, and transformed by heat and pressure over millions of years. Brine pools, with their anoxic conditions and their abundant bacterial life, are a modern example of this process in action. By studying the Orca Basin, scientists can learn about the conditions that led to the formation of petroleum deposits. They can see how organic matter accumulates in anoxic environments. They can measure the rates of burial and preservation. They can build models that help us understand where oil and gas might be found. The Orca Basin is not just a scientific curiosity. It is a natural laboratory for understanding the Earth's carbon cycle, and it is a window into the geological processes that have shaped our planet. Let us now consider another aspect of brine pools that we have not yet explored in detail: the technology that allows us to study them. Exploring a brine pool is not easy. They are deep, they are dark, they are under immense pressure, and they are often located in remote parts of the ocean, far from the nearest research vessel. The first brine pools were discovered by accident during surveys for oil and gas. The instruments that detected them were sonar and temperature probes lowered from ships on long cables. But to truly study a brine pool, to see it and sample it and understand it, you need to go there. And that requires submersibles. The Johnson Sea Link, the submersible that made the first exploration of a brine pool in the 1970s, was a small, cramped vessel capable of carrying 2 scientists and a pilot to depths of up to 3,000 feet. It was a remarkable machine for its time, but it was limited. It could only stay underwater for a few hours. It could only carry a limited amount of scientific equipment, and it could only explore the shallowest brine pools. Today, the technology has advanced dramatically. Remotely operated vehicles, or ROVs, can descend to depths of over 6,000 meters. They are connected to the surface by a long cable, which carries power and data. They are equipped with high-definition cameras, robotic arms, and a wide array of scientific instruments. They can stay underwater for days at a time, exploring the seafloor in detail. The ROVs used for brine pool exploration are among the most advanced deep-sea vehicles in the world. The Jason, operated by the Woods Hole Oceanographic Institution, is one example. It is equipped with sonar, cameras, and sampling equipment. It can collect water samples, sediment cores, and biological specimens. And it can transmit real-time video to the surface, allowing scientists on the ship to see what the ROV is seeing. Another is the Hercules, deployed from the EV Nautilus, which was used to discover the Jacuzzi of Despair. But even with the Jason and other advanced ROVs, exploring brine pools is a challenge. The brine is dense and corrosive, and it can damage the ROV's instruments. The chemical gradients at the interface of the pool can interfere with the sonar and the cameras, and the bodies of dead creatures lying at the bottom of the pool can be disturbed by the ROV's thrusters, stirring up sediment and reducing visibility. The scientists who study brine pools have developed specialized techniques to overcome these challenges. They use slow, careful movements to avoid disturbing the pool. They take samples at precise depths, using bottles that can be sealed at the desired location. They collect sediment cores, carefully extracting the layers of material that have accumulated at the bottom of the pool. And they bring their samples back to the surface, where they can be analyzed in laboratories. The water samples are tested for salinity, temperature, and chemical composition. The sediment cores are dated and analyzed for organic content. The biological specimens are studied under microscopes and their DNA is sequenced. Every sample from a brine pool is a piece of a puzzle. Each one tells a little more about the chemistry and biology of these strange environments. And together, they are building a picture of a world that we are only beginning to understand. One of the most exciting developments in brine pool research is the use of autonomous underwater vehicles, or AUVs. These are robotic submarines that operate independently, without a cable to the surface. They can be programmed to follow a specific course, mapping the seafloor and collecting data as they go. And they can explore areas that are too dangerous or too remote for ROVs. In 2019, a team of scientists from the University of Texas and the Monterey Bay Aquarium Research Institute used an AUV to map the brine pools of the Gulf of Mexico in unprecedented detail. The AUV was equipped with a multi-beam sonar system, which could map the seafloor with a resolution of just a few centimeters. The data it collected revealed the brine pools in stunning detail. The shapes of the pools, the depth of the brine, the structure of the sediment around them. The AUV also carried a chemical sensor, which could measure the salinity and temperature of the water as it flew over the seafloor. The sensor detected the boundaries of the brine pools, showing where the normal seawater ended and the brine began. It was like drawing a map of an invisible world. The data from the AUV surveys has been used to create detailed maps of the brine pools of the Gulf of Mexico. These maps are helping scientists understand how the pools form, how they evolve, and how they interact with the surrounding environment, but there is still so much we do not know. We have only explored a fraction of the brine pools that exist in the world's oceans. We have only sampled a fraction of the organisms that live in and around them. We have only begun to understand the chemistry and biology of these extreme environments. The future of brine pool research is bright. New technologies are being developed that will allow us to explore deeper, sample more precisely, and analyze more thoroughly. New expeditions are being planned to the most remote and least studied brine pools. And new questions are being asked. Questions that would have been unimaginable just a few years ago. What lies at the bottom of the deepest brine pools? What organisms live in the hottest, saltiest, most extreme environments? What can the chemistry of the brine tell us about the history of the ocean? What can the biology of the extremophils teach us about the potential for life beyond Earth? These are the questions that drive brine pool research, and they are questions that we are only beginning to answer. Let us pause now. Let the image of the Orca Basin settle into your mind. The wide, shallow depression on the seafloor, the layer of bacteria living at the interface between the brine and the seawater, the chemical gradients, the energy flows, the invisible processes that sustain this hidden ecosystem, and then let that image expand. Think of all the other brine pools scattered across the ocean floor, each one a separate world, each one with its own chemistry, its own biology, its own history, each one waiting to be explored. The brine pools of the world are a frontier of science, of discovery, of understanding, and we are only at the beginning of the journey. But even as we explore, we must also protect. The brine pools are fragile. They are vulnerable to disturbance from human activity. The deep sea mining that could extract the metals from the Red Sea pools. The oil and gas drilling that could puncture the salt deposits that feed the Gulf of Mexico pools. The bottom trawling that could destroy the microbial mats at the edges of the pools. We have a choice to make. We can treat the brine pools as resources, to be exploited for their metals and their chemicals, or we can treat them as treasures, to be studied and preserved for their scientific value. The decision we make will determine whether these strange and wonderful places survive for future generations to explore. Let us hope we make the right choice. Let us hope that the brine pools, with their deadly waters and their living edges, their preserved bodies and their thriving communities, will be there for our children and our children's children to discover. Let us hope that we can find a balance between our need to explore and our need to protect. Because the brine pools are not just scientific phenomena. They are part of the heritage of our planet. They are a reminder of the complexity and beauty of the natural world, and they are a challenge to our understanding of life itself. Before we leave, let us consider one more aspect of the brine pools that is often overlooked. The organisms that live in these extreme environments are not just curiosities. They are a resource, a living library of solutions to biological problems. The extremophiles of brine pools have evolved proteins that function in high salt, high pressure, and low oxygen. These proteins are of enormous interest to biotechnology companies. They can be used in industrial processes that require extreme conditions. They can be used to develop new drugs, new materials, and new methods for cleaning up pollution. Consider the enzyme called a halophilic protease. It is a protein that breaks down other proteins, and it functions in high salt concentrations. In a brine pool, this enzyme allows the bacteria that produce it to digest organic matter in water that would denature most other enzymes. For a biotechnologist, this enzyme is a tool. It can be used in industrial processes that require high salt, such as the production of certain chemicals or the treatment of saline wastewater. Enzymes from brine pool extremophiles have been used in the development of new detergents, which can work in cold water and high salt. They have been used in the production of biofuels, where they help break down plant material into sugars that can be fermented. They have been used in the pharmaceutical industry, where they help synthesize complex drug molecules, and the potential is just beginning to be realized. Most of the organisms that live in brine pools have never been studied. Most of the enzymes they produce have never been characterized. The brine pools are a vast, unexplored reservoir of biological diversity, and the biotechnological applications that await discovery are almost certainly enormous. But there is another aspect of brine pool biology that may be even more important. The study of extremophiles is teaching us about the limits of life. and that knowledge has profound implications for the search for life beyond Earth. When we send probes to Mars, or to Europa, or to Enceladus, we are looking for signs of life. But we do not know exactly what to look for. We do not know what forms life might take on other worlds. We do not know what conditions it might be able to survive. By studying the extremophiles of brine pools, we are learning about the range of conditions under which life can exist. We are discovering that life is far more adaptable than we ever imagined. We are finding organisms that can survive in salt concentrations that would kill most cells, in pressures that would crush most organisms, in temperatures that would boil or freeze most life forms, in the complete absence of oxygen. This knowledge is shaping the design of our instruments for space exploration. We are building sensors that can detect the chemical signatures of extremophile life. We are developing methods for sampling and analyzing environments that are similar to brine pools. We are training our scientists to recognize the signs of life in extreme environments. And when we eventually find life beyond Earth, it may look a lot like the organisms that live in brine pools. It may be small. It may be simple. It may be adapted to conditions that we would find uninhabitable. But it will be life. And the discovery will change everything. Let us now take a moment to think about the brine pools of the Pacific Ocean. Because there, too, these strange environments exist, and they have their own stories to tell. The Pacific is the largest and deepest ocean on Earth. It covers more than a third of the planet's surface. It contains the deepest trenches, the most active volcanic zones, and the most extensive seafloor spreading centers. And beneath its waters, in basins and depressions across the ocean floor, brine pools have been found. Off the coast of Costa Rica, in the Pacific, scientists have discovered brine pools associated with methane seeps. The brine in these pools is cold and rich in methane, which provides energy for chemosynthetic communities. The seeps are home to fields of tube worms, clams, and mussels, all of which rely on the methane for their survival. In the Sea of Japan, brine pools have been found in the deep basins of the Yamato Ridge. These pools are relatively shallow compared to the ones in the Mediterranean and the Gulf of Mexico, but they are no less interesting. They are fed by salt deposits that were laid down during the Miocene period, when the Sea of Japan was a shallow, restricted basin. And in the Indian Ocean, near the coast of Oman, brine pools have been discovered in the Makran subduction zone. These pools are associated with mud volcanoes, similar to the ones we saw in the Gulf of Cadiz. The brine is rich in methane and other hydrocarbons, and it supports dense communities of chemosynthetic organisms. Every new discovery adds to our understanding of brine pools. Every new pool that is studied reveals something new about the chemistry, biology, or geology of these extreme environments. And every new pool reminds us of how much we still have to learn. There are brine pools in the Arctic Ocean, formed by the freezing of seawater in the same way as the Antarctic cryogenic pools. There are brine pools in the Black Sea, where the anoxic conditions preserve organic material in exquisite detail. There are brine pools in the Caspian Sea, in the Persian Gulf, in the waters around Indonesia. Wherever there is salt and water and a depression in the seafloor, there may be a brine pool. And wherever there is a brine pool, there is a world waiting to be explored. The global distribution of brine pools is a map of the Earth's hidden geology. It shows us where salt deposits lie beneath the seafloor. It shows us where tectonic activity has created fractures and faults. It shows us where the chemistry of the ocean is being shaped by the deep Earth. And it shows us that the ocean is not a uniform place. It is a patchwork of different environments, each with its own character, its own rules, its own inhabitants. The brine pools are among the most extreme of these environments, but they are not the only ones. There are hydrothermal vents, cold seeps, methane hydrates, and deep-sea coral reefs, all of them adding to the diversity of the deep. The ocean is more complex than we ever imagined, and the more we explore it, the more we realize how little we know. Let these thoughts carry you now as our ascent continues. The brine pools of the world scattered across the ocean floor, each one a separate world, each one holding its own secrets. The Pacific pools, the Indian Ocean pools, the Arctic pools, all of them connected by the global ocean, all of them part of the same planetary system. We have not visited all of them tonight. We could not. There are too many, and they are too far apart. But we have visited enough to understand something important. The brine pools are not just a curiosity. They are a window into the deep earth. They are a reminder of the power of salt and water and time, and they are a testament to the adaptability of life. Let us now consider the chemistry of these pools in a little more depth, because the chemistry is what makes them so deadly and also what makes them so fascinating. The salt in a brine pool is mostly sodium chloride, the same chemical compound as table salt. But it is not just sodium chloride. The brine contains a complex mixture of dissolved ions, each one contributing to the unique properties of the pool. There are calcium ions, which make the water hard and can precipitate out as calcium carbonate, forming the white crusts that line the edges of many pools. There are magnesium ions, which affect the density and viscosity of the brine. There are potassium ions, which are essential for life but toxic in high concentrations. There are sulfate ions, which can be used by bacteria as an alternative to oxygen for respiration. And there are trace elements, lithium, which is used in batteries and in the treatment of mental health conditions, strontium, which is used in fireworks and in the production of certain types of glass, barium, which is toxic to most life but can be used by some bacteria as a source of energy. The combination of these ions creates a chemical environment that is unlike anything else on Earth. And it is this chemical environment that determines what can live in the pool and what cannot. The organisms that live in brine pools have evolved specific adaptations to deal with the high salt. Some of them, known as halophiles, actually require salt to survive. They have proteins that only function in high salt concentrations. They have cell membranes that are reinforced to prevent water loss. They have internal mechanisms for pumping salt out of their cells to maintain the right balance of ions. Other organisms, known as halotolerants, can survive in high salt, but do not require it. They have more general adaptations that allow them to cope with a range of salinities. They are the generalists of the brine pool world, able to live in the gradient between the brine and the normal seawater. And then there are the organisms that live at the very edge of the pool, in the zone where the brine mixes with the seawater. These organisms are not adapted to high salt. They are adapted to the gradient itself. They exploit the chemical energy that is released when the two waters mix. This energy is the key to the productivity of the brine pool margins. When the brine meets the seawater, the difference in chemical composition creates a kind of battery. Electrons flow from one water to the other, and organisms can capture that flow to power their metabolism. It is a form of energy that is completely independent of the sun. It is energy from chemistry from the earth itself. And it is this energy that sustains the microbial mats at the edges of the brine pools. It is this energy that allows the bacteria to grow and reproduce in the darkness. It is this energy that forms the base of the food chain that supports the worms and the clams and the fish. The chemistry of brine pools is not just a subject for scientific study. It is the foundation of an entire ecosystem. It is the reason why life can exist in a place that should be completely dead. Let us think about this for a moment. The energy that powers the brine pool ecosystems comes from the earth itself. It is geothermal energy, chemical energy, the energy of the planet's interior. It is a reminder that life does not need the sun. It can be powered by the earth. This has profound implications for our understanding of life in the universe. If life can be powered by the earth, then it can exist on planets and moons that are far from any star. It could exist in the oceans of Europa, beneath the ice of Enceladus, in the caves of Mars. It could exist in the darkness, in the cold, in the silence, powered only by the chemical energy of the planet itself. The brine pools are a model for life beyond Earth. They show us what is possible. They expand our imagination, and they also teach us something about death. Because the same chemistry that powers the living also preserves the dead. The bodies of the creatures that fall into the brine are preserved because the chemistry of the pool prevents decay. The salt dehydrates the tissues. The lack of oxygen stops bacterial growth. The stillness of the water prevents disturbance. In a brine pool, death is not an end. It is a transformation. The body of a fish, preserved in the salt, becomes a record of its life. It becomes a fossil in the making, a permanent record of a creature that once lived in the deep. And in that preservation, there is a kind of immortality. The fish that died in the brine pool will not decay. It will not be forgotten. It will remain intact and recognizable for as long as the pool exists. Thousands of years, perhaps millions, We do not usually think of death this way. We think of it as an ending, a dissolution, a return to the elements. But in a brine pool, death is a freezing, a stopping, a preservation. The dead do not return to the elements. They stay as they were, frozen in time. There is something beautiful in this, despite the horror of the death itself. The brine pool is a place where time stops, where the past is preserved, where nothing is lost. And perhaps that is why we are so fascinated by these places, because we all want, in some way, to be preserved, to be remembered, to leave a mark that lasts beyond our brief lives. The brine pools offer a glimpse of that possibility, a world where nothing decays, nothing is forgotten, nothing is lost. Let us now return to the ascent. The surface is still far above us, but we are rising steadily. The darkness around us is beginning to change. There is a hint of blue in the black, a suggestion of light. But before we break through to the surface, let us look back one last time, not at the brine pools themselves, but at what they represent. The brine pools are a boundary. They are a line between life and death, between the living and the preserved, between the world of oxygen and the world of salt. They are a place where the rules change, where the familiar laws of biology no longer apply. And they are a reminder that the world is full of boundaries. Boundaries between light and dark, between warm and cold, between the surface and the deep. Boundaries that we cross every day without thinking. But the boundary of a brine pool is different. It is invisible. You cannot see it until you cross it. And once you cross it, you cannot go back. That is the nature of the brine pool. It is a trap. A beautiful, deadly trap, hidden in the darkness of the deep. And yet, it is also a refuge. For the organisms that have adapted to it, the brine pool is a safe haven, a place where they can live without competition, without predators, without the pressures of the outside world. The brine pool is both a death trap and a sanctuary. It kills the unadapted and protects the adapted. It is a filter, separating the weak from the strong, the ordinary from the extreme. And in that, it is like many other environments on Earth. Every habitat is a filter. Every environment selects for certain traits and against others. The brine pool is just a more extreme example of this universal principle. But it is also something more. It is a window into the deep Earth. It brings material from the planet's interior to the surface. It reveals the chemistry and biology of the deep. It connects us to processes that are normally hidden from view. When we look into a brine pool, we are looking into the Earth itself. We are seeing the salt that was deposited millions of years ago. We are seeing the water that has been trapped beneath the seafloor for thousands of years. We are seeing the organisms that have adapted to conditions that existed on the early Earth. The brine pool is a time machine. It takes us back to the origins of the planet. It shows us what the world was like before life, and what it might be like after. And that is why brine pools matter, not just for their scientific value, though that is enormous, but for what they teach us about ourselves, about our place in the world, about the nature of life and death and time. The brine pools are not just a phenomenon, they are a mirror. And in that mirror, we see our own reflection. We are like the fish that swim into the brine. We are drawn to the unknown, to the strange, to the mysterious. We cross boundaries that we should not cross. We venture into places that are not meant for us, and sometimes we pay the price. The deep ocean has claimed many lives. The brine pools have claimed many more. But we keep going. We keep exploring. We keep pushing the boundaries of what is possible, because that is what we do. That is what it means to be human. And the brine pools, with their deadly waters and their preserved bodies, are a monument to that drive. They are a reminder of the price of exploration, and they are a challenge to continue. There are many expeditions being planned right now to explore brine pools that have never been seen by human eyes. In the coming years, scientists will descend to the deepest basins of the Mediterranean, to the unexplored trenches of the Pacific, to the ice-covered seas of the Arctic. They will carry with them new instruments, new technologies, and new questions. One of the most anticipated expeditions is the International Ocean Discovery Program's project to drill into the salt deposits beneath the Mediterranean seafloor. This project, known as the Messinian Salinity Crisis Drilling Program, aims to recover samples of the salt that was deposited when the Mediterranean dried up 6 million years ago. The salt may contain ancient brine, trapped in the crystals for millions of years, and that brine may contain living organisms preserved in the salt since the time of the dinosaurs. Another project, led by the National Oceanic and Atmospheric Administration, is planning to map every brine pool in the Gulf of Mexico. Using advanced sonar and autonomous underwater vehicles, the project will create a comprehensive map of the brine pools, showing their locations, sizes, and characteristics. The map will be used to identify the most scientifically valuable pools for future exploration. And in the private sector, companies are developing new technologies for exploring the deep ocean. Submersibles that can dive to the deepest trenches, robots that can sample the most hostile environments, sensors that can detect the faintest chemical signatures of life. The future of brine pool exploration is bright. Every year we discover new pools, new organisms, and new insights into the workings of the deep earth. The brine pools are one of the last frontiers on our planet, and we are just beginning to explore them. But as we explore, we must also remember what we have learned. The brine pools are fragile, they are vulnerable, and they are irreplaceable. Each pool is unique, with its own chemistry, its own biology, its own history. Once a pool is disturbed, it may never recover. The scientific information it contains may be lost forever. This is the challenge of our time: to explore without destroying, to learn without harming, to push the boundaries of knowledge while protecting the things we study. It is a difficult balance, but it is a necessary one, because the brine pools are not just a resource for science. They are a part of the natural heritage of our planet. They have been there for thousands of years, and they deserve to be there for thousands more. Let us also remember that the brine pools are connected to the broader ocean. They are not isolated features. The water that flows into them comes from the sea. The organisms that live around them are part of the deep sea ecosystem. The sediments that accumulate in them are a record of the ocean's history. When we study a brine pool, we are not just studying a pool. We are studying the ocean. We are studying the Earth. We are studying the interconnected system that sustains all life on our planet. And that is why the brine pools are so important. They are a microcosm, a small world that reflects the larger world, a place where we can see, in miniature, the processes that shape our planet. The salt that feeds the pools is the same salt that circulates through the ocean. The bacteria that live at the edges are the same bacteria that drive the global cycles of carbon and sulfur. The sediments that accumulate at the bottom are the same sediments that hold the history of the climate. In a brine pool, we can see the Earth system at work. We can see the connections between geology and biology, between chemistry and physics, between the deep Earth and the surface world, and that is a gift of understanding, a gift that comes from the darkness, from the salt, from the strange and deadly beauty of the lakes beneath the sea. As we rise toward the surface, let us think about the scientists who devote their lives to studying these places. The men and women who spend months at sea, who descend in submersibles, who spend years analyzing the samples they bring back. They are the explorers of our time, the ones who push the boundaries of human knowledge. People like Dr. Samantha Joy, a marine biogeochemist from the University of Georgia, who has spent decades studying the Gulf of Mexico brine pools. She was part of the team that discovered the Jacuzzi of Despair. She has led dozens of expeditions to the deep sea, and she has published hundreds of scientific papers about the chemistry and biology of brine pools. People like Dr. Cindy Lee Van Dover, a deep-sea biologist from Duke University, who has piloted submersibles to the bottom of the ocean and studied the communities of organisms that live around brine seeps. She has seen things that most humans will never see. She has touched the tube worms and the mussels and the microbial mats that thrive at the edges of the brine. People like Dr. Antje Buchius, a marine microbiologist from the Max Planck Institute for Marine Microbiology, who has studied the bacteria that live in cold seeps and brine pools around the world. She has discovered new species, new enzymes, new metabolic pathways. She has shown that life can exist in conditions that were once thought to be completely uninhabitable. These scientists, and many others like them, are the reason we know what we know about brine pools. They are the ones who have risked the dangers of the deep to bring back samples and data and images. They are the ones who have spent countless hours in laboratories analyzing the chemistry and biology of the brine. They are the ones who have published their findings, sharing their discoveries with the world. and their work is far from finished. There is still so much we do not know. How many brine pools are there in the world's oceans? We do not know. We have only mapped a tiny fraction of the seafloor. The total number of brine pools could be in the hundreds or even the thousands. What organisms live in the deepest brine pools? We do not know. We have only sampled a handful of the pools that exist. The organisms that live in the most extreme environments may be unlike anything we have ever seen. What can the chemistry of brine pools tell us about the history of the Earth? We are only beginning to understand. The sediments at the bottom of the pools contain a record of climate and ocean chemistry that stretches back thousands of years. But we have only read a few pages of that book. What can the biology of brine pools teach us about the potential for life beyond Earth? The possibilities are endless. The extremophiles of the brine pools are models for the life that might exist on other worlds. But we have only begun to study them. The answers to these questions will come in the years ahead. New expeditions will explore new pools. New technologies will allow us to see deeper and sample more precisely. New scientists will bring new ideas and new perspectives. And one day perhaps we will understand the brine pools as well as we understand any environment on Earth. We will know how they form, how they evolve, and how they interact with the surrounding ocean. We will know the organisms that live in them, from the largest fish to the smallest bacteria. We will know the chemistry that makes them deadly and the biology that makes them alive. But that day is still far away. For now, we are still in the early stages of discovery. Every brine pool that we explore reveals new surprises. Every sample that we analyze contains new information. Every expedition that we launch brings us closer to understanding. This is what makes brine pool research so exciting. It is a frontier, a place where every discovery is new, a place where we are constantly learning, constantly being surprised, constantly having our assumptions challenged. And that is the spirit we should carry with us as we ascend. The spirit of curiosity, the spirit of wonder, the spirit of exploration. The brine pools have been there for thousands of years, hidden in the darkness, waiting for us to find them. And now that we have found them, we have a responsibility to study them, to protect them, and to share what we learn with the world. Let us also remember that the brine pools are not just a scientific resource. They are a source of inspiration. They remind us that the world is still full of mysteries, that there are still places that have never been seen by human eyes, that there are still questions that have never been asked. In a world that sometimes feels mapped and measured and known, the brine pools are a reminder that the unknown still exists, that there are still frontiers, that there is still room for wonder. And that is a gift that we should treasure. The brine pools will be there when we return. They will be there for our children and for our children's children. They will sit in the darkness at the bottom of the sea, preserving the past and supporting the present. They are eternal in their own way, as eternal as salt and water and time. Let us hold one more image in our minds before we leave, the image of the brine pool as a whole, not just one pool, but all of them. The pools of the Gulf of Mexico, hot and bubbling. The pools of the Mediterranean, deep and ancient. The pools of the Red Sea, rich with metals. The pools of Antarctica, cold and alive. The pools of the Pacific, the Indian Ocean, the Arctic. All of them connected by the water that fills them and the salt that defines them. Together, they form a hidden geography, a network of lakes and rivers that exists beneath the familiar surface of the ocean. A world within the world, a secret that the Earth has kept for millions of years. And tonight, you have visited that world. You have traveled to its lakes and its rivers. You have seen its dead and its living. You have learned its chemistry and its biology. You have experienced its strange and deadly beauty. That knowledge is now part of you. It changes how you see the ocean. It changes how you see the planet. It changes how you see life itself. And that is the true gift of the brine pools. Not the data they provide or the resources they contain, but the way they expand our understanding of what is possible, the way they challenge our assumptions, the way they remind us that the world is more complex, more mysterious, and more wonderful than we can imagine. Before we complete our ascent, let us take one last dive. not into a physical brine pool, but into the story of how the largest brine deposits on Earth were formed. Because this story is one of the most dramatic in the geological history of our planet, it is called the Messinian Salinity Crisis, and it happened about 6 million years ago in the Mediterranean Sea. At that time, the Mediterranean was connected to the Atlantic Ocean through the Strait of Gibraltar, but tectonic forces were slowly closing that connection. The African plate was pushing northward, colliding with the Eurasian plate. The land bridge between Europe and Africa was rising, and the gateway between the Mediterranean and the Atlantic was narrowing. Eventually, about 5.9 million years ago, the gateway closed completely. The Mediterranean Sea was cut off from the Atlantic Ocean, and what happened next was unprecedented in the history of the Earth. Without the inflow of water from the Atlantic, the Mediterranean began to evaporate. The climate at that time was warm and dry. The evaporation rate was high. And the Mediterranean, which holds about 3.75 million cubic kilometers of water, began to shrink. As the sea level dropped, the connection to the Black Sea was also cut off. The Mediterranean became a closed basin, like the Dead Sea today, but on a much larger scale. And as the water continued to evaporate, the salt that was dissolved in it began to precipitate. First, the calcium carbonate came out of solution, forming layers of limestone. Then, the calcium sulfate precipitated, forming layers of gypsum. And finally, the sodium chloride precipitated, forming layers of halite, or rock salt. The process continued for about 700,000 years. During that time, the Mediterranean Sea dried up almost completely. The sea level dropped by over a kilometer. The basin became a series of shallow lakes, each one more salty than the last, and layer after layer of salt was deposited on the seafloor. By the time the crisis ended, over 1 million cubic kilometers of salt had been deposited. In some places, the salt deposits were over 3 kilometers thick. It was one of the most dramatic geological events in the history of the Earth. And then, about 5.3 million years ago, the Strait of Gibraltar reopened. The Atlantic Ocean rushed back into the Mediterranean in a catastrophic flood. The water fell over the land bridge in a waterfall that was hundreds of times larger than Niagara Falls. The basin filled rapidly, covering the salt deposits with seawater. Today, those salt deposits are still there, buried beneath the sediment of the Mediterranean seafloor. And they are the source of the brine that feeds the brine pools we have explored tonight. When seawater seeps down through the sediment and reaches the salt deposits, it dissolves the salt, becoming saturated with it. The brine then flows upward, following cracks and faults in the seafloor, until it emerges at the bottom of the ocean. And there it collects in depressions, forming the brine pools. The Messinian Salinity Crisis is not just a historical curiosity. It has ongoing effects on the Mediterranean Sea. The salt deposits are still dissolving, slowly releasing brine into the deep basins. The brine pools are still forming, still evolving, still creating their unique environments, and the salt itself is still moving. Because salt is less dense than the sediment above it, it tends to rise. It pushes upward, forming salt domes that can deform the seafloor. These domes create the depressions that collect the brine. They are the engines that drive the formation of the brine pools. The story of the Messinian Salinity Crisis is a reminder that the Earth is dynamic, that the surface we see today is just a snapshot in time, that the processes that shape our planet are ongoing, and that they can have dramatic effects on the chemistry and biology of the ocean. It is also a reminder of the power of salt. Something as simple as sodium chloride, a compound that we sprinkle on our food, can reshape the geology of an entire sea. It can create environments that kill. It can preserve organisms for millions of years. It can feed ecosystems that exist in the darkness of the deep. Salt is not just a seasoning. It is a geological force, a chemical agent, a biological filter. It shapes the world in ways that we are only beginning to understand. And the brine pools are the most dramatic expression of that power. They are the places where salt reveals itself in its most concentrated form, where it creates lakes within the ocean, where it kills some forms of life and supports others, where it preserves the past and shapes the present. Let us now think about the salt in our own bodies, the sodium and chloride ions that circulate in our blood, that allow our nerves to fire and our muscles to contract. The salt that we need to survive, but only in the right concentration. Too little salt and our bodies fail. Too much salt and our bodies fail as well. The brine pools teach us about balance, about the delicate equilibrium that life requires, about the narrow range of conditions under which we can survive. And they teach us about the consequences of imbalance. The fish that swim into the brine and die, the bodies that are preserved in the salt, frozen in time, the communities of organisms that thrive at the edge in the gradient between life and death. Balance. It is the key to everything. The balance between salt and water, between oxygen and anoxia, between the living and the dead. The brine pools exist at the edge of that balance. They are the places where the equilibrium tips, where the conditions become too extreme for most forms of life, where the rules change. And that is what makes them so fascinating. They are the edge, the boundary, the place where the familiar world ends and the unknown begins. Let us imagine one final time what it would be like to actually visit a brine pool. Not through a camera, not through the eyes of a submersible's robotic arm, but in person. To descend in a small vessel to the bottom of the ocean, to see the shimmering surface of the brine pool appear in the lights of the submersible, to watch the bodies of the dead resting at the bottom of the pool like fallen leaves. The approach to a brine pool is a strange experience. The water around you becomes clearer. The particles that normally float in the deep ocean, the marine snow that drifts down from above, seem to disappear. The water becomes almost perfectly transparent, as if the salt has somehow purified it. Then you see the surface. It is not like the surface of the ocean, with its waves and its chop and its endless movement. It is like the surface of a lake, smooth, flat, reflective. It shimmers in the lights of the submersible, mirroring the darkness above it. As you descend closer, you can see the details. The edge of the pool is marked by a white crust, a line of salt that has precipitated out of the brine where it meets the normal seawater. The line is sharp, as if drawn by a ruler. On one side, the normal seafloor, brown and soft. On the other side, the basin of the brine pool, filled with perfectly clear, deadly water. And there, on the bottom of the pool, you see the bodies. Fish, mostly. Some are small, no larger than your hand. Others are larger, the size of your arm. They lie scattered across the white salt crust, perfectly preserved, their scales still reflecting the light, their eyes still open, their fins still extended. They look as if they died only moments ago, frozen in the last instant of their lives. But they have been there for years. Some of them have been there for decades. The salt has preserved them completely, stopping decay, stopping time. There is something deeply unsettling about seeing a perfectly preserved fish at the bottom of a brine pool. It looks alive. It looks like it should swim away at any moment. But it does not move. It cannot move. It is frozen in the salt, a permanent record of a life that ended at the edge of a deadly lake. And yet, even as you look at the dead, you notice movement at the edges of your vision. The microbial mats. The living communities that thrive where the brine meets the seawater. They are not dead. They are very much alive. They are growing, metabolizing, reproducing. They are the other side of the brine pool, the side of life in the midst of death. The contrast is stark. The dead bodies inside the pool, the living mats at its edges, the sharp boundary between the two. It is a reminder that life and death are not always separated by time. They can be separated by inches, by a line of salt, by a difference in density. And you, in your submersible, are a visitor to both worlds. You are separated from the brine by the steel hull of your vessel, by the technology that keeps you alive in this hostile environment. But you are also connected to it. You are seeing it. You are experiencing it. You are bearing witness. The experience of visiting a brine pool is not just scientific. It is emotional. It is philosophical. It forces you to confront questions that you do not normally think about. What is life? What is death? What is the boundary between them? And what happens when that boundary becomes visible, physical, real? The brine pool answers none of these questions, but it poses them, it presents them, it makes them impossible to ignore. And that is perhaps the most important thing about brine pools. They are not just objects of study, they are mirrors. They reflect our own questions back at us. They force us to think about things we would rather not think about, They challenge our assumptions about the nature of life and death and the universe. There is a reason why brine pools are so captivating. It is not just their strangeness. It is not just their beauty. It is the questions they raise, the questions that have no easy answers. As we ascend now, let us carry those questions with us, not as burdens, but as gifts. Because questions are the beginning of understanding, and the brine pools, with their silent waters and their preserved bodies, are full of questions. Why does life exist? What conditions are necessary for it? What conditions destroy it? What is the relationship between life and the environment? How far can life be pushed before it breaks? We do not know the answers. Not all of them, but we are learning. And every time we visit a brine pool, every time we study its chemistry and its biology, every time we sample its waters and its sediments, we learn a little more. The brine pools are patient teachers. They have been there for thousands of years. They will be there for thousands more. They do not care whether we learn from them or not. But if we choose to learn, they have much to teach. There is one more concept that is worth understanding before we leave the brine pools behind. It is a concept that scientists use to describe the interface between the brine and the normal seawater. It is called a chemocline. A chemocline is a boundary between two layers of water that have different chemical compositions. In a brine pool, the chemocline is the place where the density and salinity change most dramatically. It is the invisible wall that separates the world of oxygen from the world of anoxia. It is the line between life and death. The chemocline of a brine pool is not a simple line. It is a zone, a thin layer, sometimes only a few centimeters thick, where the chemistry of the water changes from normal seawater to concentrated brine. Within this zone, there are gradients of salinity, temperature, oxygen, and nutrients. And it is within these gradients that the most interesting biology happens. The organisms that live at the chemocline are specialists. They are adapted to the specific conditions of the gradient. They can tolerate the rapid changes in salinity and chemistry that would kill most other organisms. And they have evolved to exploit the energy that is released by the mixing of the two waters. The chemocline is a place of constant activity. Chemical reactions are happening at the interface. Energy is being released, nutrients are being cycled, and the organisms that live there are taking advantage of it. In some ways, the chemocline of a brine pool is like the surface of the ocean. At the surface of the ocean, sunlight drives photosynthesis, creating the organic matter that supports the entire marine food web. At the chemocline of a brine pool, chemical energy drives chemosynthesis, creating the organic matter that supports the brine pool ecosystem. The surface of the ocean and the chemocline of a brine pool are both boundaries. They are both places where the world changes. They are both places where life is concentrated and abundant. But they are also very different. The surface of the ocean is a boundary between water and air. The chemocline of a brine pool is a boundary between water and water. The surface of the ocean is illuminated by the sun. The chemocline of a brine pool exists in permanent darkness, and yet both are essential to the functioning of the Earth system. The surface of the ocean drives the global carbon cycle. The chemoclines of brine pools drive local biogeochemical cycles. Both are places where energy is transformed and life is sustained. The study of chemoclines in brine pools has helped scientists understand other environments on Earth. The chemocline of the Black Sea, which separates the oxygenated surface waters from the anoxic deep waters, is similar in many ways to a brine pool chemocline. The chemoclines that exist in lakes and estuaries, where fresh and salt water mix, are also analogous. By studying the chemoclines of brine pools, scientists can learn about the processes that occur at all of these boundaries. They can understand how energy flows across chemical gradients. They can see how organisms adapt to changing conditions. They can observe the interactions between chemistry and biology in real time. And the lessons learned from brine pool chemoclines can be applied to other fields of science. The study of microbial communities at chemoclines has led to new insights into the evolution of metabolism. The study of chemical reactions at chemoclines has improved our understanding of the global carbon cycle. The study of energy flows across chemoclines has informed our search for life beyond Earth. The chemocline is a concept that connects the brine pools to the rest of the Earth system. It shows that the brine pools are not isolated anomalies. They are part of the broader fabric of the planet, connected by the flows of energy and matter. And the chemocline is also a metaphor. It is a reminder that the most interesting things often happen at boundaries, at the edges, at the places where one world meets another. The boundary between waking and sleeping, the boundary between consciousness and dreams, the boundary between the known and the unknown. We are at that boundary now. As our ascent continues and the surface draws closer, we are suspended between the deep and the shallow, between the darkness and the light, between the world of the brine pools and the world of our ordinary lives. The ascent is a slow process. It takes time to rise from the depths, time for the pressure to decrease, time for the darkness to fade. And in that time, there is space for reflection. Let us think about what we have seen. The brine pools of the Gulf of Mexico, with their hot, bubbling waters and their preserved bodies. The rivers of brine in the Mediterranean, flowing across the seafloor like liquid glass. The metal-rich pools of the Red Sea, holding treasures that could reshape economies. The cold pools of Antarctica, teeming with life beneath the ice. The mud volcanoes of the Gulf of Cadiz, erupting brine from the deep earth. The ancient basins of the Mediterranean, holding time capsules of the planet's history. Each of these places is unique. Each has its own story. Each has taught us something different about the nature of brine pools and the life they support. And together, they form a picture of a hidden world. A world of salt and death and life. A world that exists alongside our own, beneath the familiar surface of the ocean. A world that we are only beginning to understand. Let us also think about what we have not seen. The brine pools that remain undiscovered. The organisms that have not yet been found. The chemical reactions that have not yet been observed. The mysteries that have not yet been solved. The ocean is vast. The seafloor is largely unexplored. And every expedition to the deep brings new discoveries. The brine pools we have visited tonight are just a fraction of what exists. There are thousands more, waiting for someone to find them. And when they are found, they will reveal new secrets, new species, new chemistries, new insights into the workings of the earth and the limits of life. The future of brine pool exploration is full of promise, and we are lucky to live in a time when that exploration is happening. When scientists are descending into the deep to bring back samples and images and data. When the secrets of the brine pools are being revealed, one expedition at a time. Let us hold that thought as we continue our ascent. Let us feel the cold water around us, the pressure that has been our companion through this journey. Let us look back one last time at the depths we have explored, the lakes of brine, the rivers of salt, the bodies of the dead, preserved in the darkness, the communities of the living, thriving at the edge of death. We are ascending now. The lights of our submersible are the only illumination in a world of absolute darkness. Outside the viewport, the water is black. It has been black for the entire journey, except when we turned our lights toward the seafloor and saw the white crust of the brine pools, the shimmering surfaces of the lakes, the bodies of the creatures that did not make it back. But now, as we rise, the blackness begins to change. It becomes less absolute. A hint of blue, a suggestion of light. Far above, the surface of the ocean is waiting, with its warmth and its air and its familiar world. But we are not in a hurry. There is no need to rush. The ascent takes time, and that time is a gift. Time to let our thoughts settle. Time to let the images of what we have seen sink into our minds. Time to let the stillness of the deep become a part of us. The brine pools are still down there. They will always be down there. Their surfaces will shimmer in the dark. Their waters will sit in perfect stillness. Their edges will be lined with the bodies of creatures that wandered too close. And at their margins, the microbial mats will continue to grow. The bacteria will continue to metabolize. The loricifera will continue to swim in the salt, living their tiny lives without oxygen, without light, without any of the things we associate with life. They do not need us. They do not need the sun. They do not need the air. They exist in a world that is completely separate from ours, a world that follows different rules, a world that has been there for thousands of years before we ever knew about it. And that is what makes the brine pools so profound. They are a reminder that the earth is not one world, but many. That beneath the familiar surface of things, there are hidden realms, secret places, environments that challenge our understanding of what is possible. That life is not a single thing, but a spectrum, a continuum, a set of possibilities that we are only beginning to explore. The brine pools are a mirror. They reflect our own ignorance back at us. They show us how much we do not know about our own planet. They humble us with their strangeness, their beauty, their absolute indifference to our concerns. And yet, they also connect us, because the salt in a brine pool is the same salt that is in our blood. The water is the same water that falls as rain and flows as rivers and fills the oceans. The chemical elements are the same elements that make up our bodies. We are not separate from the brine pools. We are part of the same planetary system, the same cycle of elements, the same story that began billions of years ago. When we look into a brine pool, we are looking into the past. The water in the deep pools has not changed for tens of thousands of years. The sediment on the bottom has been accumulating since before the last ice age. The bodies of the creatures that lie in the salt are preserved as they were on the day they died. The brine pool is a moment frozen in time, a snapshot of the Earth's history, preserved in the stillness of the deep. And when we look into a brine pool, we are also looking into the future, because the lessons we learn from these extreme environments will help us understand the limits of life and where it might exist beyond Earth. The organisms that thrive in the brine are models for the life we might find on other worlds. The chemistry of the pool is a template for the processes that could create life elsewhere in the universe. The brine pools are portals. They connect us to other times and other places. They open doors in our imagination that we did not know were there. Let your mind drift now. Let the images of the brine pools dissolve into a gentle blur. The hot pools of the Red Sea, shimmering with heat, merging into the cold pools of Antarctica, frozen and still. The rivers of brine in the Mediterranean flowing across the seafloor, becoming the lakes of the Gulf of Mexico, dark and deep. The bodies of the fish preserved in the salt, floating upward and dissolving into the darkness. There is no need to hold on to any of it. The images will stay with you if they are meant to. They will fade if they are not. What matters is the feeling of having traveled to a place that most people will never see. The feeling of having touched the darkness and returned. The feeling of being connected to the deep, to the ancient, to the mysterious. You are safe. You are warm. You are in your bed, in your room, in the quiet of the night. The brine pools are far away, still sitting at the bottom of the sea, where they have always been. They are not going anywhere. They will be there for as long as the salt endures. But you have visited them, in your mind, in your imagination, in this quiet space between waking and sleeping. You have made the descent. You have seen the lakes of salt shimmering in the lights of the submersible. You have witnessed the strange and deadly beauty of the brine. Now you can let it all go. Let go of the pressure. Let go of the cold. Let go of the darkness. Let it all drift away, like bubbles rising through the water, upward and upward, toward the surface, toward the light. You are rising now. The water around you grows warmer. Above you, the darkness gives way to a soft blue glow. The surface is drawing closer. You can see the light, shimmering through the waves. You can feel the warmth of the sun filtering down. And then you break through. The air fills your lungs, warm and familiar. The sky meets your eyes, blue and infinite. The world is bright and alive, and you have returned. The brine pools are still down there, in the depths, in the silence. They will always be there, not waiting for anyone in particular, just existing as they have for thousands of years, part of the great mystery of the ocean, part of the hidden geography of our planet. But now you know about them, and that knowing changes something. It expands your understanding of the world. It adds a layer of depth to your awareness. It reminds you that there is always more to discover, always more to wonder at. Let that knowledge settle into the background of your mind. Let it become part of the quiet fabric of your awareness. The brine pools will be there in the back of your thoughts whenever you think of the ocean, Whenever you remember the strange and wonderful places that exist just beneath the surface of our world. Close your eyes now. Let your breathing slow. Let your mind settle into the gentle rhythm of the night. The brine pools are sleeping too. They have been sleeping for thousands of years. They will continue to sleep long after we are gone. But tonight, you visited them. You saw their shores. You witnessed their deadly beauty. And that is enough. Sleep now. Dream of the lakes beneath the sea. The salt will hold its secrets. The darkness will keep its silence. The brine will continue to preserve, to kill, and to remember at the bottom of the world in the quiet of the deep. There is nothing more to do, nothing more to see. The mystery remains a mystery, as it should be. You are drifting now into the gentle embrace of sleep. Let the brine pools drift away. Let the darkness release you. Let the deep carry you no further. You are floating. You are free. You are home. The lakes beneath the sea will keep their vigil alone. Rest. Sleep.